Hello my JEE champions, how are you all? So as we all remember, in my previous 3 lectures I have covered GOC1, GOC2 and GOC3. In this 3-day challenge I have completed the entire general organic chemistry that comes from the part of 11th standard. So in today's lecture we will go for 12th standard organic chemistry that involves the very first and very primary topic called as reaction mechanism. So there we go, reaction mechanism. What is a mechanism? How does mechanism proceeds and what are the categories of this mechanism? One of them is called as substitution, elimination, addition and rearrangement. These 4 basic reactions will be repeatedly seen in our upcoming chapters of 12th standard. Alkyl halide, aryl halide, alcohol, phenol, ether, aldehyde, ketone, carboxylic, amines. All of these chapter comprises these kind of chemical reactions only. So let's just start the chemical reaction. First thing that comes under mind is what is the meaning of reaction mechanism? The meaning of reaction mechanism is the step-by-step sequence of elementary reaction by which overall chemical reaction occur. That means if you are given with a chemical reaction and if this reaction is not happening in a single step, if a reaction is not happening in a single step, then how many steps are involved in this reaction? How many steps are basically containing what kind of reaction intermediates? What is the reaction, what should I say, what I forgot the name actually, substrate we call it, substrate, the reagent which we are using, and what is the product, what is the byproduct, then the stereochemistry of the product, so many things are there which comes under the part of reaction mechanism. So now first of all let me just tell you what is the general organic chemistry reaction mechanism. So organic chemistry reaction mechanism works in this way, like we are given with a reagent on which the chemical reaction will occur, and this reagent is actually called as substrate. This is none other than the reactant we call it. Substrate is basically attacked by some of the attacking reagent. This reaction proceeds with the formation of a reaction intermediate, which are nothing but the short-lived species and which will definitely or immediately convert it down into the product part. The concept of reaction intermediate is already covered in my previous lecture, where I remember GOC part 2, where I taught you about carbocation, carbanion, carbon free radical and their stabilities and the various parameters that affect their stability. So we have substrate with us, attacking reagent, reaction intermediate is formed, and right after that we receive product plus byproduct. So byproduct is something that is also called as a leaving group. In our chemistry we call byproduct as leaving group. This is the basic reaction mechanism. I'm getting aside, you people please read it out, note everything down one by one, and this will be highly helpful for your upcoming chapters of organic chemistry. So this is called as the general organic reaction mechanism, general organic reaction mechanism, general reaction mechanism. Now every single thing over here has its own importance. For an example, if we talk about the attacking reagent, this attacking reagent could be a nucleophile, could be an electrophile. Similarly, this reaction intermediate, we already have covered this part. This reaction intermediate could be a carbocation, carbanion, free radical, and this all depends upon the nature of the substrate. If the substrate is an alkane and some free radical substitution is going to happen under the influence of sunlight, then definitely the attacking reagent will be another free radical, the reaction intermediate will definitely be another free radical. So this is how the reaction proceeds. It all depends what is the nature of the substrate, the compound which we are given with, and that has to react. All depends upon this compound. Whether it is an alkene, then electrophilic addition reaction will occur. If it is a ketone, then nucleophilic addition reaction will occur. If this is a benzene or aromatic compound, then electrophilic substitution reaction occur. This is how it works. First part is reagent. What is a reagent? This is actually, let me just write it, attacking reagent. This is an attacking reagent. An attacking reagent is a species. It can be an electrophile, it can be a nucleophile. Electrophile means that loves electron, something that loves electron. That means definitely it will be having either a positive charge over that, or it will be having a complete octet which wants to accept the electron and get stabilized. Similarly, nucleophile is some species which loves the nucleus. Nucleus means positive charge. Nucleus is nothing but the positive charge. So something that loves positive charge will itself be either negative charge containing species, or it can be something with a lone pair of electrons on it. So that's how we define these two species, electrophile or nucleophile, two different chemical species. Now we have electrophile. Coming to electrophile, guys, all the cations that exist in nature, all can attack to the negative charge species and they can accept the electron pair, and they all are called as the nucleophile. They all are called what? Nucleophile. NO2 positive, NO positive, CH3 positive, Cl positive, Br positive, etc. Then we have some neutral species with cationic, the one possessing the positive charge. The neutral is the one that has incomplete octet. Neutral species are the one which contain what? Incomplete octet. So incomplete octet will be there. Take this example of BF3, 6 electrons are there. Let's see the 6 electron, 4 electron. No. SO3 cannot be the one. Okay, this might not be having an incomplete octet, but SO3 with expanded octet also can have this example. Expanded or complete octet species also come under this part, but their condition is they should be attached with an electronegative atom. Okay, let me just give you this example. Let's say C double bond O is an electrophile. This is working as an electrophile. So how does it work as an electrophile? So what will happen? Some electron density will come and attack this carbon. Why? Because this carbon is having a partial positive charge because of the presence of electrons of oxygen, or like presence of the oxygen which is more electronegative, and this electron density can shift like this. So this is how we can attack as a CO2 can be taken as an electrophile. And the same can happen with the sulfur trioxide, and sulfur trioxide has what? Vacant orbitals. So definitely if some negative charge species is coming, or let us suppose this can attack this part and electron density can shift like this. So yes, expanded octet and complete octet species can also work as an electrophile. Cationic and neutral, both of them are completed now. Now let me take you to next part called as nucleophile. So guys, whatever I'm teaching you right now, make this note in your mind that this content is extremely sufficient, not for just your JEE Main preparation, also for your advanced preparation. So keep on writing everything one by one and make yourself very confident. Solve the problems which are given inside it. Start solve the solved problem. Later on go to the one which I give you as a homework. This content will be highly sufficient for you. This will be highly sufficient for you. Doesn't require anything after that. Nucleophile. We have the nucleophile with us. The name itself suggests that these are nucleus loving species. Nucleus loving means they themselves contain the either negative charge, or they might be containing a lone pair on them, so that they can attack on the positive charge density. So now we have anionic, the very one. All anion come under this category, guys. All the anions are the part of nucleophile because all the anions contain what? What? Electron pair which can be donated. Neutral species must have at least one lone pair. Neutral species must have at least one lone pair, plus complete octet should also be there, otherwise they will not donate the electron pair. Complete octet should be there. Pi bonded species are there, pi bonded. So pi bond can also be written down as, if somewhere you have this C double bond C, so guys, this can also be represented as C with a positive charge, then C with a negative charge, and this can work as a nucleophile. See how easy is this? We have another ambidentate nucleophile. Ambidentate nucleophile are the category of nucleophile where more than one atom can attack at once. Take this example, everyone, cyanide. So if we say cyanide, so C triple bond N, and we have carbon with a negative charge. So now carbon can form a bond somewhere. We also have isocyanide. So in isocyanide also, carbon has a complete octet. I'm trying to give, this is cyanide with carbon has negative charge. Let me draw the structure of isocyanide NC, and the same structure will be there. What is happening here? See, 1 2 3, and that is normal. So in isocyanide, let's say nitrogen is bearing a negative charge and it donates there, and the structure can be represented as like that. Anyways, we are having one atom with deficiency of electron. Nitrogen has usually 5 electrons here. So 1 2 are there, one lone pair is there, that will be shifted there with a negative charge. I think this can be shown here, forming a bond between them. This can be shown there, not a problem. Dative bond. So this was an ambidentate nucleophile. We have another such example. Let me give you another such example. This is called as nitro. So the structure of nitro group is somewhere like this. So this can be donated like this, or this can also be donated like this. So this is called as, guys, nitro N when nitrogen is donating, and this is called as nitro O, or we also call nitro N as nitrite. Nitro N and nitro O. Nitro or isonitro also can be said. We have a huge theory about the nucleophiles, because nucleophiles are very important attacking reagent that will be useful in upcoming chapter, and especially alkyl halide and aryl halide chapter, where you will be using nucleophiles very frequently in their specific reactions called as nucleophilic substitution reaction, SN reactions. So anionic nucleophiles are stronger than the corresponding neutral one, and because the reason that conjugate bases are better than the nucleophile than its conjugate acid. Okay, and take this example of OH minus. OH minus is a better nucleophile than H2O. So let's say H2O is working as a base or as an acid, then it will lose H positive and it will become a conjugate base. So weak acid gives you good base, and good base are always good nucleophile and mostly good nucleophile. So this is how it works. OH phenol is weaker nucleophile than phenoxide ion, alkoxide ion, and this amide. NH2 minus ion is always a better nucleophile than NH3 ammonia. Then sigma bonded nucleophile is always more stronger than pi one. As I told you that in the previous segment where we were discussing about the categories of nucleophile, we found that some pi electron sharing nucleophile were also there, but they have distributed electron density, and that is why sigma has higher strength as a nucleophile. All the negatively charged species are nucleophilic, but all positively charged species needed not to be nucleophilic. So why is it so? Let me tell you this part. Let me just mark it as a positive, as a star. Why is it so? Because see, hydronium ion has already completed its octet. It might be having a lone pair, but it cannot accept any further electrons because it might be having a positive charge, but it is completing its maximum possible number of bonds. The same applies over here, ammonium ion and hydronium ion. So H2O is stronger nucleophile than OH minus? Absolutely no. False. False. See, how many are nucleophiles in given ion or molecule? So we have to find out the number of nucleophile. H3O positive is neither a nucleophile nor an electrophile because it is already having complete bonds with oxygen, and it cannot further accept any other electron pair. So it is nothing. ZnCl2 can accept the pair of electrons, so I can call it as an electrophile because of the vacant d orbitals present inside zinc. Then we have, what do we have? ZnCl2, Zn2 plus is also nothing. It has a complete octet, but yeah, 4s orbitals are available in order to form the bond. Let me just call it as an electrophile. CO2 is also working as an electrophile connected with the oxygen, which is electronegative and will abstract the electron density from carbon, leading carbon to get the positive charge and being attacked by a nucleophile. SO3 is also an electrophile. I have not seen any nucleophile till now. Yes, pi electron density can attack somewhere, so this is a kind of nucleophile we are having. Also, this is also called as the pi electron nucleophile. So we have two nucleophiles among us, three electrophiles, and one is the one which is neither electrophile nor nucleophile. Now one question is here, what are conjugate acids and bases? So very easy guys, whenever any acid is there, let's say this is an acid. So whenever an acid loses its H positive and gives you an anion, the so formed anion is called as the conjugate base. So in the similar way, if let me just give you the complete example. Let me react two reagents, one of them is an acid, another one is a base. So the working of an acid is to lose the H positive, the working of a base is to accept the H positive. This is called as Bronsted-Lowry theory, which explains acids and base on the basis of who can lose it or who can accept it. So this is actually an acid, Bronsted acid. This is an actually Bronsted base, and once hydrogen chloride leaves the electron, this H positive is accepted by NH3. It forms Cl minus and NH4 plus. NH4Cl is the product here. So acid plus base, this gives you anion which is conjugate base. Similarly, this will be conjugate acid. This is the acid base theory. Then we have next question, why all positively charged species cannot be electrophile in nature? As I told you, take this example everyone. This is an ammonium ion which not just has the complete octet with it, but also doesn't have any orbital left to be accepted the electrons by any other negatively charged species. So it is having complete octet. Can't accept electron pair. That is the reason. Which of the following molecule functions as an electrophile? It is an electrophile. This is having a lone pair. This is a nucleophile. Water is a nucleophile, weak nucleophile. R2NH is a strong nucleophile. Both A and B is galat. None of these is correct. We are talking about the electrophile. D is correct. Which of the following statement is not correct for a nucleophile? Ammonia is a nucleophile, true. Nucleophile attacks on low density side, low electron density means positive charge, right? Electrophile is a Lewis base, true. Lewis acid can't be true because Lewis acid is something which is electron donor. Let me write it. Lewis base is an electron donor. I have completed this part in the ionic equilibria, Lewis acid, Arrhenius acid, and then we had another Bronsted acid base theory. A Lewis acid is something that is electron acceptor, right? Now we have another basic term to discuss with. This is called as, we call this term as solvent. Initially we were discussing about the basic attacking reagents, electrophile, nucleophile. Now we have solvents with us. What is the meaning of a solvent? Solvent is something that is the medium in which we are carrying out the chemical reaction. We all know that the reactions of organic chemistry are not carried out in the open air. Definitely they require some medium, and this solvent can sometimes be water and sometimes it can be some organic solvent also. So what options are available as solvent? Let us discuss about it. We have non-polar solvent and polar solvent. The meaning of non-polar solvent, the one which have a zero dipole moment. Somebody which is some molecule which has zero dipole moment will be considered as a non-polar molecule. We have polar, that means mu will be equals to non-zero. Then in non-polar, the options are N-hexane, benzene, carbon tetrachloride, and then we have carbon disulfide. These are the available options for non-polar. Then we have polar also. Then what comes under the polar category? The polar are the one where net dipole moment is not zero. They could be polar protic, which has replaceable hydrogen, such as water. Okay, water can be termed as this HOH. So this hydrogen is available there. We have ROH. This hydrogen is available. We have acid, RC double bond OH. We have acids with us. So these all come under the category of polar protic. Then we have polar aprotic. What is the meaning of aprotic? That they cannot furnish H positive, but they are polar in nature. Take this example, everyone, like acetone, DMF, DMA, DMSO, etc. Ethers also come under this category. So what are these? I will explain it later, but let me just write the names first of very all. So now we'll discuss each and every category in very detail. First of all, let us discuss about the polar protic. As I told you, the examples could be alcohol, water. The very good part is they have the ionizable hydrogen with them. It can work as a poor acid, but yes, they have furnishable H positive, and this is the example of polar protic. These plenty examples given over here are the example of polar aprotic solvent. What is the meaning of aprotic? Aprotic means they cannot furnish H positive frequently or very easily. We have H positive, we have acetone. So acetone cannot have any acidic hydrogen, no acidic hydrogen. Basically no acidic oblique furnishable hydrogen. There is no furnishable hydrogen. The examples are acetone, dimethyl sulfoxide, dimethyl ether. Then we have dimethyl formamide, DMF, which is formamide. Dimethyl formamide means nitrogen is connected to 2 methyl atom, and then this is formamide. Amide group is there, NC double bond OH. If CH3 is attached here, it will become acetamide. So see, DMA, dimethyl acetamide. This is called as dimethyl sulfoxide. These are the same only. Note del minus is concentrated. Del minus is concentrated on oxygen, but del plus is distributed. Hence, polar protic solvent will be effectively interact with the cation but not with the anion. Very important part right now which we are discussing. These type of molecules can easily interact with the positive charge species, such as, take this example guys, CH3, C, not C, let it be C also. This O minus can easily attached with a electrophile containing the positive charge. But if something contains a negative charge, that will not be easily bound with this could be because of the steric reasons also, that a nucleophile with a negative charge, and this is positive, this is negative, not easily surrounded or not easily bonded. So this is something which we'll see in upcoming topics, where we'll see the strength of nucleophiles in different kind of medium. Let me take you to first example, the effect of solvent on nucleophilicity. We right now are discussing with a very important topic called as nucleophile. Nucleophile is a bigger topic than electrophile. Nucleophile has vast number of category under it. Effect of solvent. Solvent can be water, solvent can be polar aprotic, it could be non-polar also. So depending upon different type of solvent, let us discuss the nucleophilicity, means strength of a nucleophile, which one can be called as a strong nucleophile, which one called as a weak nucleophile. So guys, sodium halide is one of the example. Whenever it is given or it is basically dissolved in water, it gives you Na positive and X minus. X minus being a negative charge species wants to donate this electron pair present over it, and it will become neutral. So this is called as nucleophile. Now this nucleophile can be easily surrounded in water. Nucleophile is easily surrounded in water, hydrated in water, and can form an H bonding, and so does with the sodium ion. So whether it is an cation or it's an anion, both of them can be easily surrounded by the polar protic molecule, which is one of the example is the water. So strength will become what? As the electron density increases, everyone. Okay, so strength of dipole interaction is directly proportional to electron density of an ion. So as we go down the group, the size increases and size increases. Since the size increases, electron density decreases and the strength of ion with dipole interaction decreases. Thus it will become more stronger nucleophile. It can easily move in the water and can attack to the substrate. So thus its nucleophilicity is more and it can easily attack. So the example correct answer will be F minus, Cl minus, Br minus, and then F minus. It was expected that fluoride should be the stronger nucleophile because it has higher electron density. But what will happen in water? The fluoride ion can make the easily dipole moment with the water molecule. The only ion which is available for attacking over the substrate are those which are not making too much interaction with the water molecule, and these are bigger sized ions which are I minus, and that is why fluoride is weaker here and iodide is a good nucleophile over here. Next we have nucleophilicity in polar aprotic. We all know about polar aprotic. What polar aprotic solvents are? Polar aprotic solvents are actually where is polar aprotic? Polar aprotic solvents, we all know their nature, and they can easily hydrate. They can easily hydrate the hydrate or solvate. Sorry, not hydrate, solvate the cation, but they cannot do the same with anion, and that's why if they cannot surround the anions, that's why the one which will be having higher electron density will easily go and attack on the substrate, because they are not interfering with the anions. They want like anion, go anion, we don't want to interact with you, because they do not have that positive charge available on the sulfur atom that much, or it is sterically surrounded, cannot easily interact with that. So a nucleophile are free now, they are not caged, and that is why more is the electron density, higher is the nucleophilicity. The correct order in this medium will become F minus, Cl minus, Br minus, I minus. This thing is something which can be asked in your examination, and it is asked frequently in previous examination. So I would like to ask you to simply learn it, that fluoride is a stronger nucleophile than iodide in polar aprotic, but in polar protic solvent, iodide is the best among all the halide ions. Which among the following is a polar aprotic solvent? What do you think? Aprotic are the one which cannot furnish ionizable hydrogen. So ether will be the correct answer. The structure of ether is ROR. No acidic hydrogen is there, but ethanols are ROH, and that is why ROH. This H is having ionizable hydrogen in them. Okay, we have question. Choose the correct statement about the following molecules. This is having a furnishable hydrogen. I would go for this is polar, not prolar. It's simply polar. Polar protic. Not proptic, yaar. Protic. And this is polar. Why it is polar? Because it is having hydro-oxygen in them. So definitely mu is non-zero. But no furnishable hydrogen. Aprotic. So I told you once that ethers are the polar aprotic solvent. Now pick the correct answer. One can act as a pure, no. One can act as polar aprotic, no. Compound 2 can act as polar protic, no. Yeah, polar protic, yes. Compound 1 and 2 can act as polar protic. Compound 1 and 2 can act polar aprotic, no. I think B is correct. Which of the following is or are polar aprotic solvent? What do you think? Aprotic. So aprotic are polar also, where mu is non-zero, but also no furnishable hydrogen, no ionizable or furnishable hydrogen. Now we have nucleophilicity versus basicity, a very important, very widely used topic, because what happens if we talk about the basicity and nucleophilicity, both sounds the same only, because bases also should have electron density to attack upon the H positive, and nucleophile should also have the electron density to attack upon the electrophilic center, or nucleophilic center, the one where electron density is lesser or positive charge is there. So the difference, what is the difference? The difference is simple, that a nucleophile attacks upon the carbon atom. Y minus as a nucleophile leads to substitution here. See, X minus is removed and the position has been acquired by the Y atom. So another thing is called as basicity. Basicity is the tendency of an electron rich species to attract or to abstract a proton. So it attacks upon the hydrogen, and there it was attacking upon the carbon. So the sum of the same species can behave as an electrophile as well as a base. So guys, generally, very generally, the good nucleophiles are good base. Let me just write it. Generally, good nucleophiles are good bases, and vice versa, that good base will also become good nucleophile. It happens generally, but exceptionally to can be done with anything. Exceptions are like the part of chemistry, and they can happen with anything. So now we are comparing the basis, nucleophilicity and basicity. So across the period, if we go left to the right, it follows the same order. Base and acids are the same order. See, CH3 minus NH2 minus, this is the order of both basicity and nucleophilicity. Basicity and nucleophilicity, both. We all know that HF is stronger acid than water, then ammonia, and then methane. If you remove one hydrogen atom from there in the form of H positive, the remaining anion will become a base, conjugate base, and that base is also a nucleophile, and they both follow the same order of strength. When a negative charge is on the atom, the nucleophile order is parallel to the basic order. If a negative charge is there, guys, then usually the negative charge species are stronger nucleophile, and a stronger nucleophile as well as stronger base also. So take this example. These all are the examples of good basic strength and nucleophilicity also. Acetate is a very stable anion. then phenoxide, then hydroxide, then ETO minus. ETO minus is most unstable because in ET provides it a positive I effect and forming O as more negative charge. More is the electron density, more will be the basic strength and nucleophilicity as well as. But when a negative charge is on the same atom but steric crowding is operated, okay. Now see, now we have come to the point where you will find a very star point, a very important point, that basic strength will increase, but there because see, they need to attack upon the hydrogen atom only, they can do it easily, but they have to attack upon the electrophilic center. So this with a partial positive charge, it's very difficult to attack on this carbon, and this carbon is feeling the hindrance. So because of the hindrance, the correct order becomes opposite. See, nucleophilicity versus basicity, they are now working opposite to each other. Let us solve some questions. So across the period, the order of basicity and nucleophilicity remains the same. True. Across the period, we have CH3 minus, let's say, a good base, a good nucleophile as well, carbon. Then we have nitrogen. Higher is electronegativity, higher is the stability of the anion. Then I also have explained this part in basic strength, the previous one I taught you. Then we have oxygen with a negative charge, and then we have fluoride with a negative charge. This is the order of both basicity as well as and nucleophilicity. Now a general order of nucleophilicity is there, general order, and let us say if there is not mentioned what medium are we using, then always consider in aqueous medium. If not mentioned any medium, then consider as aqueous medium. So in aqueous medium, water will be the worst, because water will not allow water molecule, another water molecule, to move as a nucleophile and got attacked by the, or got attacked over the substrate. SH minus is the best, then cyanide, iodide, hydroxide, and 3 minus is called as azide, bromide, phenoxide, then we have acetate, chloride, fluoride, ROH, and then water. I remember when I was in my coaching time, similar kind of order was explained by my sir also, and he taught me this, that सफलता की सनक इंडिया और हॉलैंड की आज़ादी को बर्बाद कर रही है फोकट में, ऐसे तो कोई फंसे अल्कोहलिक पानी में. That was a Hindi version of this mnemonic, but wasn't so helpful to me by that time also. I usually learn in this way only, like SH minus not being so much surrounded by water molecule can go easily and attack over the nucleophilic center. Okay, then we have some example. Which of the four is the basic strength order? So basic strength is very simple to explain. You just add one hydrogen over there, so they will become what? HF, HCl, HBr, and then we have HI. So after losing one H positive, this forms F minus. After losing one H positive, this forms Cl minus. Losing one H positive, it forms Br minus. And losing one H positive from here, it forms what? I minus. So guys, we all know what is their acid strength order. HCF is weaker than HCl, is weaker than HBr, and this is the order of acidic strength. So definitely this opposite will become the basic strength, Kb. Weak acid forms the stronger conjugate base, and stronger conjugate or stronger acid produces weak conjugate base. The correct order of nucleophilicity in above one, I said ki if nothing is mentioned, always consider aqueous medium. When, if you are not given with the medium, So correct order of nucleophilicity, SH माइनस द बेस्ट, सफलता की सनक, इंडिया और हॉलैंड की आजादी को बर्बाद कर रही है, वैसे तो कोई फंसे अल्कोहलिक पानी में। दिस इज द ऑर्डर। Which of the following is true about a true statement? The same species can behave as a nucleophile as a base. True. Species acting as a nucleophile attack on positive. True. Species acting as a base attack. True. I think all of them are correct. B is the correct answer. So NN idea is saying that please teach analysis before January. Tomorrow is my day. Tomorrow is the day, and we'll create one community post, and in Telegram also will promote it. Tomorrow I'll teach you complete salt analysis, right? Complete salt analysis at once. So what do you think that nucleophilicity in polar protic solvent, does it decrease in the group, increase in a period, not affected, or increases in the group? Nucleophilicity in polar protic solvent, in a group we are talking about, no? Nucleophilicity in a polar protic solvent, water, so it increases down the group because F minus has Cl minus better than it, Br minus, and then I minus. Are not increase in the period, yaar. Increase in the group only. I just wanted to write. D is the correct answer. So then we have another important parameter here called as leaving group. Okay. So what is the meaning of leaving group? Whenever a nucleophile attack over the carbon and something departs with a negative charge, this is called as a leaving group. So if your base attacks someone the hydrogen, then elimination reaction will occur, and then X minus again is called as the leaving group. So leaving group is actually nothing but the byproduct. This is actually byproduct. So guys, this nucleophile, this leaving group, poor bases are good leaving group. This is something that you should remember all the time. Poor bases or also poor nucleophiles also. If a nucleophile is weak or base is weak as a leaving group, then it will be a good leaving group. It will give you a stable product. So let us say this example, how to find the order of leaving group ability. So as I told you that leaving group ability, Lg ability, is directly proportional to the stability of leaving group. So what you can see is the stability is, we all know that this is the acidic strength, and then they, after losing the H positive, they will form this one. This is the poor base will become what? Poorest base will become what? The most stable leaving group. There are some of the very good leaving group are there, which are excellent leaving group, and the one of them is the alkyl triflate, OTF. So triflate is the best leaving group, everyone. So alkyl triflate, why is it the best? Because after losing this, R goes as a positive charge, O minus comes as a negative charge, and it is the most stable anion. Most stable anion in the forms of resonance is there, an electron withdrawing group CF3 is there. This will stabilize the anion. Then we have tosylate, brosylate, alkyl mesylate, so methylase group is there. There's one more O, S double bond O, and then we have an NO2 group. This is called as nosylate. So if you talk about these stabilities among all them, so which will become alkyl nosylate is right now. So if you want to ask me which of them is the most one, so let me check. Yeah, there is an order, by the way. So there is an order directly given here, so I don't need to explain this part again. Azide is the most easily leaving group because it will form nitrogen gas. After leaving the part, it will form nitrogen gas. So let's say this is how it is connected. So this will attacked by there. So R plus plus nitrogen gas, and which is more stable molecule. Then we have triflate, brosylate, nosylate. Okay, even more than that we have nosylate. I don't know how to write nosylate. O minus MS will become O minus nosylate. ONS, nosylate. So kindly please remember this part. These two can never be. These are the poorest leaving group. Poorest leaving group, because these two are good base and nucleophile also. So learn this. This is very important and useful order. Write this order down, and allow me just couple of minutes. I'll come back with a water bottle. I'm feeling very thirsty. Couldn't manage to get the water. And please like the session, everyone. Those who haven't liked the session till now, please do the like. Yes guys, so I hope you all have gone through this order, which is very important as I told you. And now I come up with two cups of water. So hopefully, yeah. Now we'll move forward from here. So there are some poor living group that can be converted into good living group. Sometimes what happened, we have been given with the poor living group, and if we get them protonated sometimes, or sometimes we get them attacked by the such group, the previously we showed you these kind of group which are very stable anion, and somehow we get them reacted with the given compound, they become good living group. Take this example, I protonated it has become OH2, it's a good living group. It can easily leave down as a water molecule. So water molecule is a good living group. R plus with the cation you will be getting. Similarly, we have been given with ROH, and we can react it with the TSCl, which is tosylate. So tosyl chloride. What is tosyl chloride, by the way? This is tosylate group. O minus, let's say. Then I can directly where are we going to connect it here? This is a alkyl tosylate. So RO is there. RO is the no, and then here is it. Okay. Now see, let's say this is a group. This is the TS group we are saying, and then it is chloride. So what will happen initially? ROH and this, it will form this compound with removal of HCl. And finally, we know that this compound is highly stable. This can easily provide you R positive with a negative charge on oxygen. And this is tosylate ion. This is good. So which among SH minus and Br minus is better living group? The one which is stable. SH minus forms H2S, which is a weak acid. And after removing H positive, it gives you SH minus. So HS minus is a strong base. Br minus on the comparison, if we talk about the HBr, which is a strong acid already, on losing H positive, it will give you Br minus, and Br minus is a weak base. So weak base is a good living group. So it is the better living group. Br minus is the correct answer. B. Now we have to arrange the following ions or molecules in the increasing order of their living group ability. CH3 minus, NH2 minus, OH minus, F minus. So the one which is stable, this is a homework for you. Instead of doing here, I want you people to do at your home only, and let me just move forward, okay? Because I have covered few of them. Now it is up to you. How can you do it? The correct order of living group ability in a nucleophilic substitution reaction. Correct order of living group ability in the nucleophilic substitution reaction. So what do you guys think? Which is the most stable anion? I guess this is the correct answer. Acetate ion is a resonance stabilized. Br minus is a big sized anion. Cl minus is relatively smaller from Br but bigger than OH minus, and OH minus is a strong nucleophile, or we can say it's a strong base. So strong base, that means poor living group. Poor living group. अरे यार What's wrong? Anyways, let me just re-explain this part to you. Talking about their acids, we have HBr, HCl, CH3COH, and then we have H2O. We are not supposed to use that kind of information here because we attempted it wrong. So guys, this is the order of acidic strength, opposite. This is the order of acidic strength, Ka. So now after losing H positive, it will give you Br minus. After losing H positive, it will give you Cl minus. We have CH3COO minus, and then we have OH minus. Out of these, what do we see? This will become the order of Kb, and this is the leaving group ability. This is the leaving group ability. Sir, a weak base is always good. Yes, definitely. Always. A weak base will always be a stable, or we can say good or better leaving group. So that's how we compare. Choose the correct statement. Weak bases are better leaving group. As I told you, you also asked me, one of the students, true. Leaving group ability of conjugate acid is more than the conjugate base. Leaving group ability of conjugate acid is more than its conjugate base. I don't know, I didn't get this point. Leaving ability of this halogen, leaving group ability of halogen. No, I don't think so. Hi is the stronger one, so it's true. Correct. Leaving group is always true. I think all are correct, but I'm not sure what is it saying. Leaving group ability of conjugate acid is more than its conjugate base. We'll come to that later. We have type of organic reactions now. So guys, welcome to the reaction mechanism part, where 4 major category reactions are treated here. We already have covered the very important, very basic part of this chapter, that is reaction mechanism and what are attacking reagents. Electrophile, nucleophile. Nucleophile has a vast theory among them. We all have discussed all the points related to that. Now we have come to what? We have 4 type of major reactions. Nucleophilic substitution, electrophilic substitution, theoretical substitution. Elimination reactions are also like that. So elimination reactions are E1 reaction, E2 reaction, E1cB reaction, EI reaction. Then we have addition reactions. Then addition reactions are nucleophilic addition, electrophilic addition, theoretical addition. Rearrangement reactions are also very important reaction. Carbocation itself has a rearrangement. Pericyclic rearrangement. We have Bachmann rearrangement. We have pinacolone rearrangement. So rearrangement itself is a very vast topic, but our major target of the day is to finish these two: substitution versus elimination. These two are very important, we frequently use. Addition or rearrangement reactions are not that big, and there will be some applications which will be used directly in the chapter itself. But substitution elimination is very frequent reaction, will be seen so many times in upcoming chapters, especially in the 12th class organic chemistry. I will lead you first of all to the SN1 reaction. So anyways, let me just give you this idea, everyone. There I will cover 4 type of reaction: unimolecular nucleophilic substitution, bimolecular nucleophilic substitution, intramolecular nucleophilic substitution, and NGP, neighboring group participation. Then in elimination, I will also deal with 4 important parts of elimination: E1, E2, E1cB, EI. So this is what our target of the day is to cover with. And if you are ready, then I will start from the very first. If we can complete these all, our chapter will be completed. Reaction mechanism will be completed. So guys, those who haven't liked the session, please like it immediately. and hopefully I'm delivering what you people are asking. Your one of the very demanding chapter of analytical chemistry will be taught you tomorrow. I will teach that analytical chemistry tomorrow. So we have SN1 reaction, guys. So nucleophilic substitution reaction, unimolecular substitution. See, S substitution, N nucleophilic, and then uni. Actually, we should go reverse, and then it will become a meaningful term that unimolecular, one molecule involves only unimolecular nucleophilic substitution. So this reaction is also called as solvolysis because solvent itself works as a nucleophile. This is how the reaction look like. What happens? Step 1. In the very first step, we are using a polar protic acid. We are using a polar protic solvent here. So this is a polar, this is partial negative, this is partial positive, and this bond wants to break. This is the transition state where it is showing like it is about to break. Then this is how it went. Carbocation is a reaction intermediate here, and the first reaction only part is the what should I call it, RDS. This part is actually slow, so this reaction is only the rate determining step. So what is the meaning of rate determining step? So the one which is the slowest step of a reaction, that is the only step which decides the complete mechanism of a particular process. So if the slowest step is given to us, we have to decide everything using slowest step. So let's say the product of slowest step is a carbocation. So now higher is the stability of that carbocation, higher will be the rate of reaction. So we need to check whether which one of them will do the easier SN1 or faster SN1, the one which is giving us the stable carbocation. So now see and check it out. The presence of a polar protic solvent helps to dissociate the carbon bromine bond, because this is carbon has a positive partial and this is negative partial charge, and since the solvent stabilizes the carbocation and Br minus ion. In the next step, everyone, in the step 2, which is a fast step, so let me write this step is now fast. So what will happen in the fast step? Nucleophile will come and attack from two sides. So this is the nucleophile which can attack from both of the side. So let us suppose this is the front side and this is the back side, front and back. So front and back, it forms theoretically it should form 50% and 50%, and this is actually called as 100% racemic mixture. We all know racemization. Yeah. Racemic mixture, a mixture that contains D plus L form. So configuration, let's say this is D, this is L form, levorotary and extrorotary. But practically this not happens in that way, because we all know the direction from which leaving group is departing, taking the negative charge with it. In that direction, if a nucleophile comes with a negative charge, it will feel some obligations. It will not be easy to attack over there. So that is why the lead or the percentage will be slower, a bit lesser than 50% in the same side, retention, and in the inversion side it will be higher, and that is why we call this thing as we term it as a partial racemization or partial racemic mixture. So majorly it will be present in the form of inverted product only. But yes, both of them will coexist. Am I not audible properly or what? Forgot to wear it. Yaar. Somebody is asking me, sir, please reply. Beta, are you not getting what I'm trying to say? I have already replied you by that time only. The moment you asked me the question, your question was, sir, a weak base is always a good leaving group. I said, yes, beta, yes, always. and I have solved so many such questions using that practical example. Now let us come to some of the characteristics of SN1 reaction, nucleophilic substitution. So very simple reaction, nucleophile will come, leaving group will depart, but SN1 reaction has some characteristics. So like rate expression can be represented like this, substrate raised to power 1, because we know the slowest step was only departure of the leaving group from the substrate. So only thing that is involved as a reactant is the substrate. Molecularity will be 1, order of reaction will be 1, as refer the RDS, the determining step, or the slowest step of the reaction. And then there occurs the partial racemization. As I told you, the inverted product will be in higher yield than the retented product, or in the retention product. The note, the carbocation formed reacts with the available nucleophile in the non-selective step. What does that mean? Carbocation formed reacts with all available nucleophile. Okay, all available nucleophile. So guys, if you use NaI and water, so there are like two type of anions are there, Na- and also water. So both can attack as a nucleophile. Both of them are actually nucleophiles. So you will be getting all the product. We have SN1 reaction and energy profile diagram here. So energy profile diagram gives us the energetics and the process of energy, where energy was higher, energy was lower. So initially we have simple the reactants. Then reactants first leave the this thing, and they reach to the first transition state. This is your first transition state. This bond is about to break. This is called as transition state 1. Then we reach to the reaction intermediate in first step. Then we have another part where nucleophile is about to get attack. So this bond should be shown partially. This bond is not 100% formed. This is about to form. Then it is finally the product. This is the progress of reaction. But please note down this part, that if the substrate is given us in such a way where rearrangement of carbocation can take place, then yes, another product will be formed with rearrangement of carbocation. I'll take you to some of the example. But before that, there are some factors that we should study. SN1 reaction. Nature of substrate, it is always 3 degree, 2 degree, 1 degree, and stability of carbocation decides what should be the nature, which should give you the faster rate of SN1 reaction. Number 2, we have nature of leaving group. Always stable leaving group will give you the good yield. So iodide, bromide, chloride, and like that. Then we have presence of heavy metals such as silver and lead. Sometimes being a Lewis acid easily enhance the progress of this reaction. So this reaction can be enhanced in its rate of reaction by adding the Ag plus and lead minus, lead 2 plus, which help easily abstracting the X minus and forming the R positive. Then anion or the nucleophile will attack over here, forming the SN1 product. Nature of solvent, always polar protic solvent has to be used, because this is the RDS. In RDS, it stabilizes the carbocation so formed, and it helps also to form the carbocation easily. Nature of nucleophile, since RDS is independent of the concentration of nucleophile, we should use the no effect of nucleophile on SN1 reaction. But generally we prefer solvent as nucleophile, or we can say the weak nucleophile is preferred. Weak nucleophile is preferred. There are some compounds which typically give SN1 reaction. Why? Because the carbocation so formed is very stable. Let us say if it is removed, this is resonance stabilized. So we can say this is reso stable. So that this effects removes it over here from here. So this is the resonance stabilized. Then another one example is here. X minus departs, lone pair stabilizes like this. There are some typical examples which are inert toward SN1 as well as SN2, just like this, because guys, this is already having a resonance like this, not like this, like this, due to which what do we have? A partial charge over here. So if you remove this, it will give you this vinyl carbocation, and this is a sp2 hybridized carbon with a positive charge and becomes highly unstable. Then if we talk about here, not this is sp2, this has become sp, this is actually sp carbon being the positive charge, unstable carbocation. Or we can also use this fact that in both of the cases, what is happening, this halogen when departed is X minus, it forms this phenylenium carbocation, highly unstable. This is highly unstable, and so does this. After removing X plus, this is giving this, but it should be planar, because this carbon is actually sp2 hybridized, and it should maintain a bond angle of theta is equals to 120 degree, planar. But this structure is non-planar. The structure is non-planar, and this should be planar, but it is not planar. So these three are the examples which are very difficult to undergo SN1 reaction. So please remember this part. If you are not getting it, let me re-explain this part to you. So guys, if I take this example or any of the example, let us take this example, a similar kind of example you can take. So X is already there. So X is doing what? X is transferring its electron density, and it is in the resonance like this. So guys, this will look like somehow like this, and this also creates a negative charge here, and so on. But they're resonating hybrid, these all are resonating structures, so their resonance hybrid will look like this. That's our partial double bond is here, partial double bond is also here with a Cl. So this is having a partial double bond. Partial double bond does what? Not easy to break. Partial double bond is not that easy to break. That is the reality, that is the truth, that is a fact behind. It's not breaking easily. See, not breaking. And the same happens over here. Resonance, the halogen is under the resonance, will not break easily. So now we will have some SN1 reactions, some typical SN1 reactions with carbocations rearrangement in them. Now you can take this idea over here, and then I'll explain the part again somewhere. So this is your alcohol, which is another polar protic acid. In the very first step, this will be removed down, and this is called as the rate determining step or the slow step, where Br is removed, forming a carbocation. Now this carbocation is, this is your alpha carbon, this is another alpha carbon, 1 plus 3 alpha hydrogens are 4, though it is 2 degree hydrocarbon, right? It's a 2 degree carbocation with the 4 alpha hydrogen. So now if I do 1,2 hydride shift, and this shift which we have already discussed in the previous classes, in my GOC2 lecture I have discussed about the rearrangement of carbocation. Please read it out, please go through the complete series there. Complete series has the explanations. you will be getting this kind of product which has 8 alpha hydrogen and also a 3 degree carbocation. 3 degree carbocation we are getting with 8 alpha hydrogen. So this is highly stable. This will give you the final product. So this is your major product. This is your major product. And yes, the another product will also be formed from there, but that will not be major, that will be minor product. Like that. So try some of the questions from your end and then become comfortable in this particular topic. Which among the following compound undergo faster SN1 reaction? So guys, after removing this, it will give you 2 degree carbocation, but here after removing this, it will be having 3 degree carbocation. This is more stable. So A is the correct answer. The rate of reaction is directly proportional to the stability of carbocation. Another important question, which one of the following is most reactive toward SN1? Let us first draw the structures. This is having benzene with CH with another benzene and one Br group. So definitely this will form a more stable carbocation, and I think that's it. That is the correct answer only. So this is, let's say, positive charge. This will be go as Br minus. So this is reso stabilized. This is resonance stabilized. I think A is the correct answer. Okay. Now, why do 3 degree alkyl halide show SN1 compared to SN1? We all know that rate of SN1 reaction is directly proportional to stability of carbocation, because that is the RDS. RDS involves the formation of carbocation. Higher is the stability of carbocation, higher is the rate of this chemical reaction. Na 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 na. I think SN1 is now completed. So what is racemization? Racemization is a mixture of D plus L form. So D plus L form becomes the neutral form. When does the rearrangement take place in SN1? Where more stable carbocation can be achieved. SN1 reaction does what? Inversion 100%? No. Formation of carbocation? Yes. Non-polar? No. It's a polar solvent. Elimination? No. So B. Which of the following undergoes nucleophilic substitution exclusively by SN1? Which will follow? Benzyl chloride. Benzyl is CH2Cl. So guys, this is resonance stable. A is correct. Ethyl chloride. Chlorobenzene. Or I already have told that this is not easily brokeable. C is incorrect. Then we have isopropyl chloride. This also can go, but still this is the perfect answer, A. So one question was asked in JEE Main 2019. In 2019 JEE Main, this question was asked, everyone, that the major product of the following reaction will be what? So guys, first of all, we'll remove this. So this will be in RDS rate determining step. This forms a cation that look like this. Now I am pretty much confident in these questions and very much comfortable doing, and I want you people also to become like me. So this electron density will be shifted doing what? 1 to hydride shift. Why? Because what we are getting right now is a 2-degree carbocation. This can be stabilized. So this is how it will go for 1,2 H minus shift, hydride shift. I told you already have taught this part. So this will form what? CH3C. Then this will acquire a positive charge. Then it forms CH2 and then becomes CH3. Right after that, what medium we are using? CH3OH. This oxygen lone pair as a nucleophile attacks on this positive charge, and this will later on remove the hydrogen so that it will become somehow like this. OCH3 is connected, then we have CH3, we have CH2, CH3. Now tell me the correct answer, everyone. It was asked back in 2019. The correct answer should be na 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 na. Very easy questions have been asked previously in JEE Main. If we observe, there was a question that was asked in JEE Main 2022 asking us the inactive toward SN1, which can be inactive toward SN1. So guys, the one, see, this will form a positive charge here, and this is bridged carbocations are highly unstable because carbocation has sp2 hybridization. It wants to go for 120-degree angle, becoming planar, and it is already there as a sp3 right now, and it will be like that only, maintaining its existing state of 190-degree 28-minute bond angle. Bridged carbocation are highly unstable. And this is so very good for that. I think C should be the correct answer. Rest all are the good one. We have finished successfully one of the very important reaction called as SN1 reaction, and now we have entered into SN2. What are the SN2 reaction? So SN2 reaction, the name of the reaction itself suggests that it is bi molecular nucleophilic substitution reaction. 2 molecules are involved. In this reaction, what happened? It actually happens in one step only. That is why it is called as one step concerted mechanism. Rather than SN1, it was happening into 2 step. In one step, the halogen was departing. In this step, what happens? Nucleophile attacks, and then this departs immediately and simultaneously it happens. So very easy reaction. What will happen? This is OH minus, and this is not, because this is the leaving group. So leaving group also has a minus charge over there. So this is supposed to attack from the back side. This comes where? From the back side only. So if it comes from the back side, then from this side, front side, this will depart as a leaving group. And this is how the product will be got. This product is called as inverted product. This is called as inverted product. Now check it out. The bromine has left from the right hand side, and from the left side, OH is connected from. Mechanism, it's a single step, one step concentrated mechanism, but yes, it proceeds through the formation of a pentavalent transition state. It forms a pentavalent transition state. So in RDS, first step, OH minus is attacking from the back side, and this departs, Br minus departs. So this bond will be forming, this bond will be breaking, and it's a 5-valent this charge. Overall charge on this will be a -1. Check it out. And that is why sometime electron withdrawing group present over there stabilizes this pentavalent transition state and increases the rate of chemical reaction. It increases the rate of chemical reaction actually. And presence of bulky group destabilizes it. So SN1 reaction, SN2 reaction proceeds with lighter groups only. So this is the final product. Characteristics, it happens with the backside attack of nucleophile, which is called as Walden inversion. Walden inversion doesn't mean that there is a inversion of the configuration, or the R will become R, or absolute configuration will not change, or neither the D and L will change. The only change that will take place is the attack of group will take place from the opposite side of the leaving group. This is what the Walden inversion means. That's very simple. That is the very simplicity of this process. And backside attack takes place, and that is why if something very hindered is given, very hindered groups are there, then the reaction doesn't take place. And that's why the order of reaction will be 1 degree, 2 degree, 3 degree. 1 degree will give the fastest, 3 degree will not give this reaction. The reaction rate can be written down as K into substrate raised to power 1, nucleophilic raised to power 1, and that is why the order of reaction is 2. The overall order is 2 because refer the rate expression. And energy profile is very simple. It's a graph with only one peak, because where the transition state will be formed, this is your reactant, and then after one step, because it's a one step reaction, transition state will be formed, and finally you will reach to the product. So guys, nature of substrate should be a lighter one, and 3 degree alkyl halide, that is why do not give you SN2 reaction. 3 degree alkyl halide resist this reaction. The rate of reaction is inversely proportional to the steric hindrance. Inversely proportional to the steric hindrance. Then we have stability of transition state. Greater is the stability of transition state, higher is the rate of chemical reaction. Greater the stability of transition state, higher is the rate of reaction. So that is, and good nucleophile will always help you. So smaller reagent will be there, more stable will be the pentavalent transition state, which is bearing a negative charge. Iodide will be the fastest. Why? Because this is the stability of an ion, and that is what a leaving group requires. Stability of an ion is the condition required for the ability of leaving group. Lg. Nature of nucleophile. Nucleophile should be strong nucleophile so that it can attack in the one step and can remove the leaving group. Nature of substrate. Nature of solvent. Solvent should not be a polar protic. Otherwise, what will happen? Polar protic generally stabilizes the attacking nucleophile, because attacking nucleophile will get interaction with this polar molecule, and not just polar molecule, polar protic molecule. So polar protic molecule can surround the nucleophile, but which cannot surround but are polar in nature, which are polar aprotic. So DMSO, ether, DMF, acetone, these will favor the reaction of SN2. Then we have typical substrate favor SN2. So guys, which are the substrate? They will definitely go for SN2, and they can easily go for SN2. Believe me, these are also the similar one, because what is happening here, try look at this one. Try look at this one. This is sp hybridized. This is sp2 hybridized carbon. So sp2 hybridized has more electronegativity. This electronegative carbon will reduce the negative charge from the pentavalent transition state we got. So they stabilize it easily, and that's why the reaction easily attacks, easily happens there. Now next thing is also similar. Now nucleophile is attacking on the carbon atom, and there is an oxygen which is creating a -I, because these are some examples which were good in the case of SN1 also, and they are good in the case of SN2 also, because in SN1 these were very much helpful to stabilize the carbocation by resonance, and in this SN2 reaction they are very much helpful in order to abstract the electron density, abstract the negative charge from the this transition state, pentavalent transition state. So that is why they are increasing the rate of reaction. Higher is the stability of transition state, higher is the rate of chemical reaction, like that. So such examples are these. If strong electron withdrawing group is attached there on the carbon, which is actually gonna to like leave halogen, so that also helps us maintaining the stability of the pentavalent transition state. Then typical substrate which will inert toward the SN2, the same one which were inert toward the SN1 are the one. So what happens? This is involved and forms a partial double bond. So this is the partial, not this one. This is actually giving what? the partial double bond. If a partial double bond is there, this is not very easy to what should I say, to remove it. No, and the same happens here also. Again we have a partial double bond. This is sterically crowded, so nucleophile cannot easily come and attack there. Why? Steric hindrance. So these were inert towards SN1 also, and now they are inert towards the SN2 reaction also. So guys, SN1 and SN2 are very easy reactions which we have already completed. If you face any doubt, do let me know in the comment section. I'm strictly taking your doubts here, and I have not found any doubt. That's why I'm not entertaining in the terms of talking to you. Now simply come back to our concept. Among the following compound, which of them will give you faster SN2? So guys, this is what this compound, this might be 1 degree, but this is a 3 degree, but this is 1 degree, but this is actually 2 degree. So this 3 degree cause more steric hindrance. This causes more steric hindrance. So correct answer should be B. Which of the following is the least reactive toward SN2 reaction? Least reactive. Okay, let me check. See, this will after maybe man, this is good. This is 1 degree, and this is to 1 degree, and this is sp hybridized carbon, sp2. So it is actually helping in order to stabilize it. They will definitely go. But coming to this part, attacking on this carbon, which is a 2 degree, and attacking there and removing this, and attacking here. So here guys, let me write C as the option. The pentavalent transition state is highly unstable. The pentavalent transition state is highly unstable. Let me check if it is the correct answer or not. Yeah, it is. Is highly unstable. Why? Because see, what kind of pentavalent transition state will it make? Let me just draw this part. Okay. So what would it make? This will make this. This is highly unstable transition state is here. See how restricted these bonds are, very closer and all. Anyways, let's come. Now, what is the meaning of concerted mechanism? Concerted means one step. Something is happening in one step is called as concerted mechanism. What is Walden inversion? So, this is leaving group. This is nucleophile. And if nucleophile attacks on the back side, leaving it from the front side, the leaving group, this kind of is called as Walden. From this to this, reaching from this to this is called as Walden inversion. Which of the following is least reactive toward nucleophilic substitution SN2? least reactive, so will be this only towards both, because this has a partial double bond character, and partial double bond cannot be easily broken down by the nucleophile. In SN2 substitution reaction of the type RBr plus Cl minus DMF blah blah blah, which of the following has the highest relative rate of reaction? What do you think? Which of them will be having the highest rate of reaction? Tell me which of them will be having highest rate. So in SN2 type reaction, 1 degree will give you the highest rate, and that also 1 degree with smaller group. 1 degree in smaller group will give you this. So R should be what? Least crowded. As simple as that. So guys, just read it out, SN1 versus SN2, then we'll solve some more problems on this, and then we'll come to SN, NGP, or further reactions will come. Okay, allow me a moment, I'll be coming back with one coffee and then I'll continue from here. So just read it out, everyone. So I hope you all have noted these points down, and these are the very important points, not just the important point, but also the overall summary between SN1 and SN2 reaction mechanisms of nucleophilic substitution reaction. So guys, now from here I will take you to some of the very good questions involving both SN1 and SN2 reaction, and right after that we'll go for, okay, let me check with them. Here I will take you to some of the very good questions involving both SN1 and SN2 reaction. So, okay, very curious student has joined us. So, Mr. Yeah, hi everyone, hi studios, and hi Vipul. Chalo, let me continue from here. So those you people have covered these process, this part. SN1 reaction is a unimolecular reaction that requires solvent molecules only as a nucleophile to attack upon the highly crowded substrate. Highly crowded, why? Because the highly crowded substrate will give you more stable carbocation. It's a slow process. It happens into 2 steps. SN2 reaction, on the other hand, is a one-step concerted mechanism in which a strong nucleophile comes, attacks on the lesser crowded substrate to remove the leaving group, and the leaving group in both sides should be more stable only, and that's why among the halide it follows the order of fluoride, then lesser than chloride, lesser than bromide, and then highest is the tendency of iodide. Now let us solve some question. Which of the following shows SN1 easily? Allyl bromide. What is allyl? Let me draw the allyl molecule for you. Allyl is this, and okay, bromide is here. Ethyl bromide is CH3 CH2 Br. So guys, we all know that after removal of this will remove as Br minus. This is a carbocation and this is a resostable. What is it? Give you resostable carbocation, but there is no resonance in ethyl bromide. If you remove the ethyl like bromide ion from ethyl and it forms ethyl carbocation, in that carbocation there is no, what I call it, resonance, or any stability factor is not there. Try this question. It was asked back in JEE Main 2014. Question is pretty simple. In SN2 reaction, the correct order of reactivity for the following compound. It's very easy, yaar. This is what? Kind of 0 degree, 1 degree, this is 2 degree, and this is 3 degree. So correct order should be, the least crowded will give you more SN2. B is the correct answer. Try the next question. Choose the correct statement. So SN1 is unimolecular, SN2 is bi. True. Polar protic solvent require SN2, SN1, while aprotic required. True. Both SN1 and SN2 depend upon the concentration of substrate. True. Correct is D. Try this question. Find out the major product and the mechanism followed. Mark the product. So this is O minus, Na plus, and it's a strong nucleophile, by the way, and substrate is also 1 degree Rx. This favors SN2 and it is strong nucleophile. Strong nucleophile favors SN2. I think SN2 will happen. Simply OC2H5 should be the product. Then what should be the potential energy diagram for SN1? So SN1 can have as many peaks as possible, but the peaks must go in increasing order. So I think this is the correct answer. First transition state, second transition state. This is intermediate where carbocation will be formed. This is product, this is reactant. What? Okay. Wait. First transition state has the higher one. The second should be the fast. Okay. My bad. First step is the slow step. Take this thing, everyone. First step is a slow step. This is your transition state 1. This is reactant. This is product. This is transition state 2. This transition state 2, or this is your reaction intermediate. This is carbocation formed somewhere. So guys, this process is fast, this process is slow. I forgot actually, and that is why transition state 1 will be at peak. B is the correct answer. How easy question was it, yaar? How can I attempt it wrong, yaar? JEE Main 2010, you tried by your own, you submit with the correct answer, and I'm allowing you some time. Do it. Let's say who can do it. Question of the day, let's see. For this question, I'm allowing you two minutes. Start. Try it. Chalo. Anyways, end it. So we have NaOH among us, C2H5OH with us, and we need to make this stable compound. So let's say if we make a carbocation, it will be a stable carbocation. So let us say I'm following SN1 mechanism. So after following SN1, this kind of product will be obtained. Methyl group is here. Here is a positive charge, which is a reso stable. So this can do one. No. If it is already resonance stable, it won't interrupt then. Let us not interrupt its stability. Otherwise, what will happen? If you make it 3 degree by sending it here, double bond resonance will be broken down. Okay, this is what I can say reso stable already. So the next step, OH minus will come and attack, and I guess that should be the final product. Not this one. Yeah, this is CH3. This should be the final product. So this is the correct. A is the correct answer. Another question. So arrange these reactivity order of acetone and Ki. So acetone is what? Acetone is what? Polar aprotic. Polar aprotic favors what? SN2. Ki is I minus. I minus is a simple nucleophile as well as a leaving group. So let's see, I minus can attack and what it can make. This reaction is SN2 mainly. So which of them gives the SN2 reaction faster? So wherever the double bond is closer, let's say this one. So what does it do? This is your sp hybridized carbon, sp2, and this is more electronegative and can help it faster. So wherever we are getting a distance is increasing, wherever the distance is increasing of this sp2 hybridized carbon, it will become more difficult for this reaction to occur. So I guess third will be the least, second will be the highest, and D should be the correct answer. And this is your sp2 hybridized, the farthest. 1, 2, 3, and there we have one. No, I think D. No, yeah. Second and fourth is the worst. Fourth is the worst. This is okay. This has been asked in JEE Main 2021. Yeah, this is a good question, by the way. Now let me recheck it. Second is the best because second has the closest, and okay. Wait. Second might be the best, but now we have to check it that this is 1 degree. The attack is happening on 1 degree, and fourth we have 2 degree with farthest. This is the farthest sp2 hybridized carbon atom. So fourth will be the worst, second is the best, and third will come somewhere intermediate in between. So let us pick A now. But that was a good question, by the way. Believe me, like where all concepts are like struggling to each other, question becomes immediately very good, and this was a great question. So we have another question for us, SN2 reaction. So as I told you, rest of the question will be done from your end as a homework. These are very quality questions. You all have the answers for the questions also. Another such reaction is here. Very simple SN2 reaction because it's a sorry, polar aprotic, and this is strong nucleophile, and both of them follow what? SN2. So just make a single product with inverted. Br will be removed like this. SN2 attack should take place. Inversion of configuration will be seen. I think this is the only correct answer. Next type of nucleophilic substitution reaction is called as SN-NGP reaction, where NGP means neighboring group participation. Neighboring group participation. So NGP is also known as the enchimeric assistance, means nearby group assistance, means adjacent, near to it. And it's a case of intramolecular catalysis where a suitably placed nucleophile assists the another nucleophile to attack with a faster rate. NGP reactions are faster than SN1 and SN2 reaction. Neighboring group participation are faster. How much? 70,000 times faster. 70,000. So how does it happen actually? See, let us suppose some nucleophile has to attack. So before a nucleophile attacks, this makes a transition state like this. This makes a transition state like this and removes chlorine very first. So what it will make? A cyclic compound like this, where SPH is connected here with a positive charge, and one hydrogen will be there. Another chlorine has already departed, and here will be the hydrogen another. In the next step, nucleophile comes, and now it is very easy for a nucleophile to attack at some of the less hindered place. This departs like this, and the final product will be this. SPH, hydrogen and simply nucleophile. So here will be nucleophile, there comes the hydrogen, like that. So that is what the correct reaction is, and you can remove this negative charge now. Hello Sai Charan, hello. I hope this part is pretty clear to all of us. How does it work? We all know. So this can happen with both retention of configuration as well as inversion of configuration. No, both side retention is only happening. Okay, SN-NGP happens with SN, no inversion occurs, no. Because see, it is attacking on the same side. Can you see it? Cl only, same side it is attacking. Same side it is coming, see, you can examine. This side it departed, this side only it is attacked. Same side. Now, silent features of these reactions are the attacking reagent and leaving group must be anti to each other. Sorry, the NGP and leaving group should be anti to each other. Check it out. This group and this group are anti. These are present anti to each other in the same plane. NGP plus inversion, it happens retention of the configuration at final. NGP is an intramolecular SN2 reaction kind of thing. It is a proportional, the rate of reaction is proportional to the concentration of reactant only. And NGP at first, because in first step or RDS, this is the only RDS, slowest step. So there is no external molecule which is basically added here. This is the only molecule that participates in the reaction and forms this compound. So that is why the rate of reaction is only dependent upon the concentration of reactant, not upon the attacking reagent attacking there. NGP is a first order reaction. The order of reaction is first. Now, what do you think which will of the reaction will be very fast? So guys, this can cause what? NGP. This can attack here, this can remove here. So first it will go for SN-NGP. Let me tell you how does it happen. So initially it attacks there. So what will happen? See, this is the compound, and then OH minus or NaOH attacks on either of the side like this, and then this opens the ring. So this is how it will look like. This is your final product. So this rate is very faster, around 70,000 times faster than the normal SN2 reaction. Now we'll reach to the further type of this reaction. SN-NGP is very clear to all of us. So SN-NGP, choose the correct statement. NGP is first order, bilkul. NGP is faster, yes. NGP, nucleophile, and they must be anti, absolutely. All of them are correct. For any kind of doubt, do let me know in the comment section. Hi, hello is enough for today. Any kind of doubt comes, do let me know. So we have next question for us. Next type of reaction under nucleophilic substitution only is called as SNi, intramolecular nucleophilic substitution reaction. Intramolecular, so within the molecule the reaction will occur. So the most common example in this, okay, this also reaction proceeds with the retention of the configuration, because the attack of the groups takes place from the same side from which the leaving group is departing. So there we have this reaction. SNi reaction is happening here. How does it happen? This very common example over here is this. Like alcohol plus thionyl chloride alcohol with thionyl chloride produces RX alkyl halide plus HCl plus SO2, and these two are the gases. So this reaction is supposed to be the best reaction in order to synthesize the alkyl halide, because both of the byproducts are gases here. So you can check out the mechanism, what is happening in the mechanism. Initially this O-, this oxygen of alcohol attacks over sulfur, and electron has to be moved in such a way that this becomes a kind of like a transition state or kind of intermediate. O- comes back forming double bond and Cl departs. The Cl, wherever it is departing from, takes HCl, then no, this is not it is happening, no, not like that. I must say that, let me explain this part to you. This is also right. So now what happens in the next step? Next step involves this shifting of oxygen like this, removal of this, and the same side attack the wherever it is basically leaving from, it is attacking from the same side. Then it forms what? RCl plus this sulfur dioxide gas is removed. So this is your SNi mechanism. Now it is correct. I was actually missing with the last step. Now it is correct actually. Fine. So the same reaction occurs in the presence of pyridine. If the same reaction occurs in the presence of pyridine, it follows SN2 mechanism, and the reaction product will be inverted, because pyridine is often included to promote the reaction via SN2 path. So what actually pyridine does, everyone? Let me just re-explain this part. So till here it was clear. In the initial state we were clear with this part, but now what is happening with the same basically way, this hydrogen is being attacked by pyridine. This is your base. A pyridine works as a base, and whenever a base attacks upon the hydrogen, this acquires a stable molecule like this and also produces Cl minus. Now this Cl minus is available as an electrophile. Sorry, not electrophile, nucleophile. The Cl minus is available as a nucleophile. So now what does this nucleophile do? This comes from the back side, following the SN2 reaction. This group is departed like this. This is also departed like this. The final product will be, the final product is actually SN2 product. So SN2 product is attained. Okay? That is it. That is what we have to learn about SNi reaction. That's it. So now we have, which of the following substrate will not favor a nucleophilic reaction by SN1, SN2? So actually all of them do not give this reaction. This is a bridged, neither a carbocation is stable and nor it is a like it's very bulky and hindered to be attacked by SN2. This is also a very bulky part and generally resists to the SN1 and SN2 also, because even if I go for SN1, this will be 1 degree only. This is a 1 degree substrate, and same applies with PHBr also. Finally, we have come to elimination reactions. Which reactions did we finish? Substitution reactions are finished now. In substitution, how many reactions did we study? 4 type of reactions. What were they? SN1, SN2, SNi and SNNGP. Now in the similar way, in elimination reaction, we have 4 type of important reaction. 4 reactions are E1, E2, E1cB and EI. So these 4 reactions we will study, and that's how we end this topic or this chapter with. Let me see how many questions I have come up with. Do I have plenty of questions? I added some questions at the end, so maybe that will be helpful for you. Now, so elimination reaction it involves the removal of two groups, and generally one being proton and another being the some leaving group, and that forms an unsaturated compound. Okay, the elimination could be of this type, like wherever we are removing the group from. So let us suppose this is a carbon atom, and there is the hydrogen and there is the halogen, and since we are removing it from this only, this becomes what? This type of removal is called as alpha elimination. This is called as alpha elimination. Sorry. Then another could be beta elimination. So what we are doing, let us suppose this is having one of them is having hydrogen here and another one is having halogen here. So if the attack happens in such a way so that this occurs, okay, so positions you can check, positions, this is alpha and this is called as beta carbon, 1-2 positions. So alpha elimination, or we can also call it one-word elimination. This is called as beta elimination, or we also call it as 1-2 elimination, 1 or 2 elimination. So the product will become what? Again, an alkene will be the product here, and this HX will be eliminated out, byproduct. In the similar way, there could be 1,3 or 1,4 also. This 1,3 and 1,4 generally makes a cyclic compound. So this can attack here. This is what? One carbon. This is alpha, beta, and then this is gamma. So dash with gamma and then attacks over here. So this kind of attack is called as gamma elimination or 1,3 elimination. So the compound found will be, how many members are there? So 1, 2, 3, 4. 4-membered ring is there, like this, and oxygen is attached with the like that. Okay, now we'll try some of the examples here. Let's see, and individually we'll discuss. So number 1 is called as alpha. Alpha means we are removing from the one only. So 1,1 elimination. Alpha is actually 1,1 elimination. And both the groups are present on the same carbon atom. And the best example is this. This is called as dichlorocarbene formation, which is a reaction intermediate, and it is a work as an electrophile. So this OH minus is attacking on this hydrogen. Hydrogen leaves with its electron density to the carbon, and with this negative charge on it, this negative charge comes like this and departs the Cl minus, forming Cl minus and dichlorocarbene. So generally dichlorocarbene is used as an electrophile. So it might be carrying a lone pair here. You must be wondered about to see that it is carrying a lone pair, but still it is working as an electrophile because it has incomplete octet, and the species that attack on it, after attacking on a species, it will attack on an electron rich species to complete its octet. So in the presence of a base, chloroform or bromoroform undergo this reaction of formation of carbene, and this is the part of alpha elimination. Number 2 is beta elimination, which is the most important part that we have to study in this elimination part. Later on we'll come to E1 reaction, E2 reaction, E1cB reaction, and even EI reaction. All of these type of reactions belong to E2 reactions only. What is the E2? Not E2, yeah, beta elimination only, because all of them, mainly elimination reaction comes from the beta elimination. The most common example of the elimination is beta. So, and rare one is alpha and those gamma. So in this reaction, base comes, attacks on the hydrogen. So where is it? Alpha and beta hydrogen. Beta hydrogen departs with its electron density and then departs the halogen atom. So HCl is your byproduct. HNCl which is removed here, or Cl minus which is removed here as a byproduct, and this forms an alkene. So now this particular beta elimination also has so many types, which is E1, E2, E3, and the fourth one is called as EI elimination, cope elimination, pyrolysis of ester, pyrolysis of xanthates. These are the examples, comes under this category. So elimination reaction is 1,3 elimination. 1, 3 or 1n elimination means more than alpha and beta. Now we may reach to gamma, delta, eta, whatever whenever reach. So this reaction generally happens where base attacks and forms a cyclic ring. So cyclic ethers are generally formed. Let me write. What does it form generally? Cyclic compounds. Cyclic compound are formed, ethers. So now we have to start with this reaction, which is your beta elimination. So we'll discuss about the beta elimination one by one, and we'll try to cover all of the beta eliminations. So number one of beta elimination is called as your E1 elimination, and we call it unimolecular elimination reaction. One stands for unimolecular. So this type of beta elimination occurs in two steps, exactly like SN1. Just like SN1, this reaction occurs. The only difference is here elimination will take place, and there it was happening with the nucleophilic substitution. There we were using the nucleophile, and here we'll use the same molecule or same ion as a base. The first step is the RDS, where the carbon leaves the halogen and forming a carbocation. Second step is the loss of beta hydrogen and forming the E1 reaction. Here we use generally use base, which is solvent only. So exactly like SN1. Try to understand this reaction is absolutely like the SN1 reaction. So E1 reaction occurs at high temperature. Even reactions occur at high temperature. Even all elimination reactions occur at high temperature, right? All elimination occur reactions at all elimination, because there's a like departure of some group taking place in the elimination reaction, not the substitution of the groups taking place. So all elimination reactions usually occur at high temperature. So high temperature favors the elimination reaction, low temperature favors the substitution reaction, like this. So guys, take this example. Water is here. In the first step, this is removed, producing carbocation. Anyways, I'll explain this compound. This is the same molecule or different one? Different one. Okay, I'll explain this part to you, all of you, the reaction mechanism. Or we can take the previous example also in order to explain the mechanism part. The reaction is over here. CH3, CH2, CH3. This is a reaction, and we are having water, and usually they will mention heat with it. So heat helps to know us whether the reaction is elimination or what. So I will take you through the proper mechanism from here. So guys, initially this is your step 1, and step 1 is the slow process, or this is also called as the rate determining step, where the chlorine atom will be departed by itself only, without any external aid, because this is a polar protic solvent which we are using with the carbocation, and here will become the Cl minus. In next step, do you find any possibility of rearrangement? If not, then simply the water molecule will act as a base to attack upon the next carbon to it. So let us suppose this was initially alpha, so we have beta. There are so many betas, okay? This can also be beta, this can also be beta, like that. So how many compound can we make So let us suppose this is the hydrogen. Now this hydrogen has come at alpha position with respect to the carbocation. Initially with respect to chlorine, this was at beta position. So this is your hydrogen. So this is being attacked over here by this, and after being attacked, this leaves its electron density like this. So this is your final product is formed, CH3, CH, double bond, CH, sorry not CH, double bond, CCH3, whole twice, C. This is the product which we are getting. So this is a major product. What is it as a major product? Why it is a major product? Because it is more stable, and this major product is called as Sadzef alkene or Sadzef product. The another product could be, we know that there are more than one alpha hydrogens are there, even these are also alpha, sorry beta, these are also beta. So from there also it can be removed. So this can attack on this hydrogen also, leaving behind this. So there is could be another compound. This is your compound CH3, CH2, then we have C, CH3, double bond CH2. But this compound is actually a minor compound, not even stabilized, not thermodynamically stable product, and this is also called as like Hofmann alkene. So please remember this part. Let's have a look over here. Please try to follow the mechanism and try to understand like what I have just taught you using the mechanism. Reaction mechanism has been explained over here. This is called as elimination reaction, E1 reaction. Next, elimination reaction E1. Some examples. So very easy reaction, we all know. First of all, we'll remove this compound, we'll make a carbocation which is already stable. So next to it is alpha and alpha with respect to carbocation, then it will form CH3, CH double bond, CH single bond, CH3. So this will be two alkenes, cis plus trans. So trans alkene will be the major product. Along with it, there will be another alkene, CH3, CH2, CH, CH2. This is called as Hofmann alkene. Next example. So you will make a carbocation first. Already a stable carbocation, then you will form an alkene. This is your major product. Plus there will be another alkene. This is called as exocyclic, minor. This is called as endocyclic because it is within the endocyclic alkene. This will become exocyclic alkene. Bond present outside, double bond present outside of the ring is called as exo, and then endo is within. Now try solving this question. Yeah, so now I'll explain this question. I gave you enough time, maybe you people have covered it. So the first step will give you, first I'll go to step 1, where a carbocation will be formed, polar protic solvent will be used, heat is representing the elimination product, or the higher temperature gives you the same. Then we have CH3, we have a carbon here which is also containing to CH3, but this is unfortunately 2 degree carbocation. So this can be converted into 3 degree if we go for some shift here. So shifting is possible here. This shift can be done. It is called as 1,2 methyl shift, Me shift. So what we'll be getting after Me shift? CH3C. Then this methyl has shifted, acquiring a positive charge. This is CH3 already. This will be CH. Here comes the CH3. Here also CH3. So next step is to attack by the base, and that also which one? So now we have plenty of options here. This is also alpha. This is also alpha. And we know that more crowded alkene will be the major product called as ZZF alkene. So one product will be CH2 double bond C CH3 CH3 CH3. This is your Hofmann alkene, and the another one alkene will be CH3 double bond CH3. This is more crowded with more number of alpha hydrogen or hyperconjugable hydrogen. This is called as ZZF alkene. And generally ZZF alkene is the major. In E1 and E2 this will be minor. Note you down. Just note down and try to understand the mechanism, and please you make yourself comfortable in these questions because these are very important. And today I'll cover all the mechanisms possible in general that will be using in complete 12th standard. So good evening, and when will you start haloalkane and haloarene? So tomorrow we have a session on analytical chemistry that people have requested me earlier, salt analysis and practical organic chemistry. Tomorrow probably I'll teach you. Then on Monday I'll go for practical inorganic chemistry, and probably on Tuesday we'll go for hydrocarbon. Then we'll take a break from there. I have a function to attend. Later on I'll come back, and then we'll start the complete 12th standard organic chemistry. That is what the plan is. Now you try this question. The correct order of even reaction, it's very easy, that we just need to decide the stability of carbocation, because rate of reaction of SN1 and E1 both are directly proportional to the stability of carbocation, and that is what we can do. So guys, this is more resonance, which we can see, more reso. This one is less resonance, and there is no resonance as such. So this will be the order of stability, and this will become the order of even reaction. Clear? Elimination reaction, E2 reaction. So now we have come to bimolecular elimination reaction. Bimolecular elimination reaction. Earlier we were discussing about the that is E1 elimination. Now we have come to E2 elimination. So E1 and E2 both are the part of beta elimination only, because beta is the most common mechanism that we use in elimination reactions. So we'll take beta reactions and here, and so this takes place in the presence of strong base, just like SN2. Guys, have you seen this kind of similarity between SN1 and E1, and then SN2 versus E2? In SN1, when we are using a weak nucleophile, there we are in E1 we are using a weak base. In SN2 we used strong nucleophile, and here we are using a strong base. So bases could be alcoholic KOH, Na, C2H5, zoop, 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 zoop. So guys, alcoholic KOH means alcohol is C2H5OH, and alcoholic KOH is this. So they react together and they form C2H5O minus K positive plus water. So believe me, this compound which we are getting, this compound is called as potassium ethoxide, or this is also called as alcoholic KOH. And most importantly, this compound is strong base. This compound works as a strong base. Most importantly, this compound works as a strong base. So another stronger could be this where is it? NNH2 is even stronger base, sodium amide. So consider a reaction. So this reaction happens in one step only. So let me just explain this part. Actually, there are like two alkenes will be formed. One butene, no doubt, is called as your Hofmann. 2-butene is no doubt your Sadzef or more crowded. So this will become as a major product. So it has the lesser energy, that is why it is shown as lesser one. This is more energy, this is shown as transition state of path B, transition state of path A. Try it. If this is not clicking, then please try, because what I'm explaining to you is elimination reaction will occur simply at once. So I will explain this part, like what's happening here. I will consider the same example and we will all look at this, everyone. We'll all look at this. This is a molecule CH3, CH, CH3. No, CH or what? CH2 is here. One more hydrogen. We have CH, then we have a bromine here. And then we have another CH2 with one more hydrogen. So guys, you should imagine all these, and believe me, it is very easy. So I'm using a strong base here. Let us suppose alcoholic KOH we are using. We all know what is alcoholic KOH. OC2H5, negative charge. So base can attack at two possibilities. One is this, and another one is this. So where should it go? So we'll make both of the products, right? So this is, let's say this is path B, and let us say this is path A. Path A versus path B, and let us see. This is absolutely enough for your mains, advanced, and whatever the exam you are preparing for. So don't panic about the examination level. Practice should be held from your end. Try solve all the questions which are given inside, and also you bring questions for yourself. Now come back to the topic. Now this base will attack on can attack on both. The condition is they should be anti-periplanar. They are in same plane, Br, H and H, but they are anti to each other, like opposite to each other. So this base will attack onto this hydrogen also. So this hydrogen will be attacked, the leaving group will be this, and this Br departed, forming an alkene. So one product could be like this. So A alkene will be, A path is where? A path is this. So this will be your A path, CH3, CH2, CH, double bond, CH2, and this is called as Hofmann alkene. And we all know that Hofmann alkene is formed in minor quantity because it is not stable. And also there is one more point that we can add is, since it's a one-step concerted mechanism, the rate of reaction is directly proportional to the stability of the alkene formed. So it is directly depending upon the alkene formed and its stability. Now in next step what we will do, B alkene will be what? CH3, CH, double bond, okay. This is your second product. Now it is major, and because it is more crowded, it has more number of alpha hydrogen, which are like making this alkene stable, hyperconjugable hydrogen. This is called as Set-Zef alkene. It doesn't even require any what should I say, any further detailing of the mechanism, because as I told you, it's a one-step concerted mechanism. So it all happens at just once. There will be one transition state that will be like containing two negatively charged species. One is the leaving group, another is the attacking reagent, and the carbon which is gonna to release the hydrogen will definitely be acquiring a positive charge right after the proton departs from there. But anyways, we'll see like what happens. We'll see. Let us move forward then. So this is what I have told you. Reactant to product we are making, and we are having two type of transition states. Final product will be formed like this. We have elimination reaction E2 with us, and there are some properties, so just read it out, everyone. So there is called as Hofmann elimination reaction. The type E2 reaction in which the least substituted alkene is formed is called as an Hofmann elimination, and such type of elimination occurs in the following condition. So there are some conditions where base is a bulky base, such as tertiary butoxide. Tertiary butoxide is CS3, CCS3, O minus, or this could be, guys, IPR2, IPR, isopropyl, whole twice NH, or R3N tertiary. These also can be used to like as a base which we are using, and it's a bulky base which we are using. The bulky base can lead to the formation of Hofmann alkene. Similarly, when the leaving group is a poor leaving group such as fluoride, NR3 minus SR2, then this kind of reaction is actually called as, we'll deal with this later on, this reaction is called as E1cB reaction. These reactions are called as E1cB reactions. Right. Anyways, so let's see. We are given here, everyone. See, we have two type of hydrogen here. One is this one. This is your alpha. So this is your beta. This is also beta. So we have two type of beta hydrogen. One is this one, and the another one is this one. The question is which one it should attack very easily. This base can attack. This is a bulky base. What is it, by the way? This is a bulky base, and bulky base is supposed to attack upon more easily upon the terminal one, very easily. So this attack happens easily, and this is very actually difficult to attack with for a bulky base, and that's why in that way this is called as your Set-Zef alkene, the most stable alkene. Set-Zef alkene right now we are getting as minor, and your Hofmann alkene, the less substituted alkene, will become majorly 72%. So this happens only in the case of where we are using a strong base, and that too a bulky base, not strong. It should be a bulky base, because all the E2 elimination reactions carried out under strong base only. But not only strong, this is a bulky Mo2 base. Then we have third type of reaction called as E1cB reaction. Starting from here, we have completed the part of E2 elimination. Right after that, we'll solve so many questions, and all together only we have another question, another type of reaction called as E1cB, another type of elimination reaction. So the name of the reaction is elimination reaction through conjugative base, right? Let me just write it, it's not written there. So this is basically elimination. This is your elimination reaction through or via conjugate base. Conjugate base. So if the leaving group is a poor leaving group such as fluoride Nr3 plus or Sr2, or the negatively charged developed on the carbon before losing the proton, like after losing the proton, the negative charge develops, so that a transition state is formed there, which is like which is more stabilized carbon ion would give you the major product. Okay, so let us just come to the mechanism part. Where can you find it? I'll explain the mechanism using the same example only. I'll explain it. So one of the case, there was, we saw that there was a bulky group present inside it, bulky base was attacking, and number 2 could be this, and the example is very simple. Everyone try understanding this one. So this is your CH3 and we have CH over here, and the leaving group is fluorine, which is no doubt fluorine is a poor leaving group because the product formed will be F minus, and F minus is a strong nucleophile, they can attack back, and also a strong base can attack back. So CH3, then we have CH2, and then here is CH3. Clear? So how many beta hydrogens can you see? How many beta hydrogens can you see? We can also make it like CH2 H. Again, this should be periplanar. CH2, and this is also H. Anti-periplanar. So now let us suppose we are attacking it with a strong base, let's say ETO minus, alcoholic KOH. So ETO minus can have the possibility to attack onto this, also this. So let's see who decides which should it attack on. So the first thing that you will observe here, or the first compound that will be formed here will be, there could be two possibilities. The one could be this, carbon ion is formed in the first step, and this is the only the acid base reaction only will form a carbon ion. So CH2 minus CH fluoride, CH2 and CH3, and this is your hydrogen. No need of this, simply write CH2. So guys, this is the first product that you are getting, right? And the another will be CH2, CH3, CH fluorine, CH minus, and then we have CH3. Now try to understand this part. This is very important part now. This is one of your reaction intermediate. So this is more stable actually. This is actually more stable, and this gives the major product. More stable gives the major product. This is actually less stable, and the lesser stable gives what? Gives minor product. So try to form the final product out of it now. So major will be CH2 double bond, CH single bond. So now what happens? Simply this goes this and this goes this, and believe me, this is the only now what we are taking it out now. This is your RDS and slow step, and that is why we call this reaction as E1 CB. Why we are using 1 means unimolecular. And why are we calling it unimolecular? Even if we are using two things, one is the substrate, another one is strong base, we call it unimolecular because this is the RDS. After formation of carbon ion, the settlement of this negative charge and leaving group is leaving out. This is the only thing which will be causing the slowest step, RDS. So the two products formed will be CH2CH, CH2 and CH3. This is your Hofmann alkene, we all know, less substituted alkene, and Hofmann alkene is the major one. The another alkene will be ZF1 CH3, CH double bond CH CH3. This is called as ZF. And this is your minor. I think I have explained it now, and I don't think anything is left in E1cB apart from this. Is it clear to all of you or not? Okay, now let me take you to further examples. So Hofmann elimination was a good reaction we saw. We have another such reaction in which tertiary quaternary ammonium salt of strong base, quaternary ammonium salt with strong base is known as Hofmann elimination reaction. Okay guys, remember this, star marking it, Hofmann elimination reaction. So what will happen under Hofmann elimination reaction? Hofmann exhaustive reaction also we call it. So this is your alpha, this is your beta, beta hydrogen, no beta hydrogen as such apart from this, attack over here, hydrogen will take the electron density from here, there departs this group, and after departure this becomes your leaving group, this is your alkene. So why is it Hofmann, and why are we calling it Hofmann? Why not calling it the ZF? So I'll give you, this is the very easy question. Take this question also. This is the base, this is quaternary salt of ammonium, and this will attack onto, there are two possibilities. Okay, this is the best example actually we are looking for. We have two possibilities. This is some nitrogen. To this connected is called as alpha, to this connected is called as beta, this will be gamma. So this has beta hydrogen here. The another one will be like this, this is alpha, this is also beta. Only two alkyl groups are there which are having the beta hydrogen. Now this attack can happen under two sides, this or this. Now the question is, where should it attack upon? So note this thing everyone, note this thing down, that under such condition, when more than one alkyl group, you all know the product, what will the product will be formed. So just let me write the explanation and then I'll make the product. Mechanism is already known to us. When more than one alkyl group has beta hydrogen, the easily accessible oblique least hindered, or we can simply call it lighter group. Okay, least hindered is fine, or least hindered carbon with hydrogen, least hindered beta carbon with hydrogen will be eliminated, But when it happens, when more than one alkyl group has beta hydrogen, the easily accessible or least hindered beta carbon with hydrogen will give you the eliminated product, will be eliminated. So now we have two conditions here. So which can be easily? I think this is easy to access and this one is tough or difficult, isn't it? So this will be removed, this beta will not be removed, so the correct answer will become CH3, CH2, CH2, nitrogen, CH3 and CH3 plus this will be giving us CH2 double bond CH2 ethene. So ethene is your Hofmann product. That is why we are calling it as a Hofmann product, and rest will be your C2H5OH after removing the hydrogen. Now, can you understand this example? Can you understand this example, guys? This was very beautiful example. So this is your major. This is the major product, and this is the Hofmann alkane which we have received. This is called as E1cB reaction. Sir, please reply. JEE Main 60 days left. Guys, what to reply? I know 60 days are left. That is why I am like working very hard these days trying to finish all the syllabus which is pending. And I think that organic chemistry is the only syllabus which is pending from our end. So I am taking continuous lectures these days in order to finish your complete organic chemistry. Now let us solve some questions on the same. I think we have finished all the E1cB also is done. Okay, try this question. So identify the major product that is obtained on the treatment of this compound with this. So guys, let us first write the compound clearly. So this is your compound CH3, CH2, CH, there is a fluorine, and then we have CH3. So guys, we already have two type of beta hydrogen. This is alpha, this is beta, this is beta. As I told you, the most accessible will be the one will be attacked. Actually, this will form a carbon ion. So this will attack this one, right? And this will form, and then this is CH2 negative charge. So this negative charge will come here, then departs the fluorine. This is your RDS, rate determining step, and there forms the final product, this. Now try which one is the correct answer. I think this is the correct C. C is the correct answer. Another good question asked in JEE Main 2018. A very good question asked in JEE Main 2018. We are about to give the correct answer on NaOH-OMe. So guys, what is happening here? What do you see? We have no alpha hydrogen here. Sorry, no beta hydrogen. No beta hydrogen there. But yes, only this is the beta hydrogen possibility. This one is alpha. This one is beta. So this will go and attack here the hydrogen, and then elimination will occur. I think this is the correct answer. This is the only possibility. Correct? D. Next question is, which of the following statement is correct? E2 is a concerted reaction in which bonds break and new bonds are formed at the same time. I think this is true. Order of reaction of the halides will be 3 degree, true. Even for both E1 and E2, this reaction follows 3 degree, 2 degree, 1 degree. This is true, this is true. E2 reaction occurs in the presence of strong base, true. All of them are correct. There is another question asked in JEE Main 2020. But look at this. This is tertiary butoxide. So tertiary butoxide is a bulky base. Bulky base we are using. No, yaar. No. Not at all. Tertiary butanol. We are not giving it the strong base. It is working only as polar protic solvent. This is only working as polar protic solvent. This is no base. Base was tertiary butoxide. This is butanol. So this is not a base. Do not make such kind of mistake in your exam. This is just a polar protic solvent, as I can see, and rest will be decided. So what will happen? First of all, this group will be departed. So RDS says that this will be formed, and this will be formed with a positive charge on carbon atom. In the very next step, this butanol, or like whatever it is, so BuOH will attack, and we already have the most stable carbon with that. No. Once this happen, we will undergo rearrangement. So this is a hydrogen here, and this hydrogen departs and goes there, called as 1,2 hydride shift. So there happens the 1,2 hydride shift. So hydride shift results in the formation of positive charge appears here, simply like this. Now the final thing is left here to form the final compound. So in next step, we have this T tertiary B as a base. It will attack upon. There are two possibilities. One is here, one is here, one is here, and one is here, and third one is even here. Three possibilities are here, but which of them will give the most stable product? I think C. I was very right. C is the correct answer. So this is the path which is followed. So this is the most stable alkene. So actually we are not supposed to get confused about tertiary butoxide or tertiary butanol. It has plenty of time to attack upon. And that's why we are removing it from the most stable one. Now we have come back to stereochemistry of E2 reaction. So E2 reactions were discussing by that time, and meanwhile of the E2 only we introduced E1cB reaction meanwhile, and we studied E1cB also. Now what I'm doing is I am bringing the concept of E2 reaction and its stereochemistry. So where should be the groups, where should the attack comes from, who attacks on what, where. So this is what we will study under stereochemistry of E2. So beta hydrogen, which has to be abstracted, must be anti-periplanar. Very important term, anti-periplanar. Anti means opposite to each other, and periplanar means within the same plane. Within the same plane, it is called as planar, anti-periplanar. So what is the meaning of that? Take these examples. So the very one is the very common example there. What we see is that hydrogen and this L is the leaving group. Both of them are in the same plane but opposite to each other. That is the correct anti-periplanar. Here this is as dash position, and leaving group should be at the wedge position, wedge dash, wedge dash. So now these are planar but anti to each other. That is what it works. In the third one also you will see hydrogen. Since hydrogen is not on wedge and dash, it's on the planar basically bond, planar bond, plane of the bond, this board. So that hydrogen bond is in the plane of this board, blackboard, this digital board, and L leaving group is also in the plane of board only, and both are anti to each other. That is why they can be represented like so, horse projection. And finally in the Newman projection you will see the structure like this. This is anti-periplanar, same plane of board they are in, hydrogen and lithium, this leaving group, but both of them are anti to each other. So believe me, these should be anti-periplanar to each other. Now I'll come to some of the questions. Okay, don't worry, I'll come up with some of the very important questions related to this, and then you'll understand. Okay, then in E2 elimination, nature of substrate has to be asked. See, we have already discussed in detail about the E1 elimination, but now it is term of the E2 where we are discussing what reactions or what factors are required to go for faster E2 reaction. So guys, the reaction nature is, nature of substrate directly proportional to the, or rate of reaction is directly proportional to the stability of alkene. Stability of the alkene, because the reaction is happening into one step only. So the reactions which are occurring in more than one step with intermediate, they require the stability of the reaction intermediate in the rate determining step or the slowest step. Just like SN1 and E1 reaction, rate of SN1 and E1 reaction is directly proportional to the stability of carbocation. But here the reaction rate is directly proportional to the stability of final product, because it's a concerted reaction, concerted mechanism is followed. So as the number of alkyl groups at the carbon which is attached with the leaving group increases, the rate of E2 increases, because this will give the formation of more stable, stable of alkene I wanted to write, stability of alkene wanted to write, stability of alkene. Then number of beta hydrogen increases, also the alkene obtained will be more stable. As the number of anti-positioned hydrogen increases, the number of rate also increases. The higher is the cases of number of hydrogens available, higher will be the rate of this reaction. Anyone faces any doubt, do let me know in the comment section only, but please ask me the genuine doubts only, as I can see some of you are asking me unnecessary thing also. Now we have leaving groups. Leaving group is the same only. Leaving group tendency is iodide is the most common, then we have bromide, then we have chloride, and then we have fluoride, because F minus is a stronger base, and a strong base cannot be a good leaving group. A leaving group or good leaving group should be a weak base. That is how it follows. The rate of reaction becomes this. Concentration of base is directly depends upon, because we know that the reaction is directly proportional to the substrate. Substrate is your Rx, and then it is your base. So it is also dependent upon the concentration of base. So higher is the concentration of base we are using, higher will be the rate of reaction. Then we have nature of solvent. Solvent should be polar aprotic, because the strong base is usually a strong nucleophile, and that nucleophile will interact with water if it is there. But in the case of polar aprotic, they do not surround or they do not solvate the nucleophile easily or the negative charge species easily. That is why always use the polar aprotic solvent in the case of E2 elimination and SN2 also. What about the nature of base? Base should be stronger. Always use stronger base. Basicity increases the rate of reaction. Now let us solve some questions. Which type of solvent favor the E2 reaction? Polar aprotic or polar protic? Aprotic is fine. The product over here. Okay, this is some good question, guys, isn't it? We're using alcoholic KOH. This is your beta. Well, this is a anti-periplanar. Oh my god. OMG. This is the most beautiful question. If this is in dash position, so definitely hydrogen will be available in this position. Hydrogen will be available in this position. So basically we see no hydrogen is anti. Also they are planar, but still there is no anti-periplanar. No hydrogen is anti-periplanar to bromine or the leaving group. if no hydrogen is parallel or anti-periplanar to leaving group, the correct answer should be no elimination. This is my guess. I don't know the correct answer, but I think this is the correct answer. Yes, there is no elimination that will take place. No elimination occurs. No, no, no. Two bromopentane is heated with potassium ethoxide in ethanol. The major product will be what? What is 2-bromopentane? 1, 2, 3, 4, 5. We have bromo here, and simply we are using ETO minus K plus. So guys, it's a strong base and it's a lighter base. E2 elimination will occur. So this will attack onto those hydrogen where it can produce the ZF alkene. So this is your correct answer. 1, 2, 3, 4, 5, and like this. So pent 2ene, and pent 2ene will also be cis plus trans. Cis can also be formed, trans can also be formed. So now it all depends upon so cis plus trans will be, and trans will be major because trans alkene is more stable. Trans major because it is actually more stable. Next question. Which mechanism is followed in above reaction? Elimination only, but yeah, it is a what should I say, weak base. So weak base follows the even elimination. Even elimination will occur. Now what do you think? What do you see that dehydrohalogenation product will be what? So check it out, everyone. We all have studied this part. Then let's suppose this is in dash. So in this is the compound actually, and what I found in this compound is there is no anti-periplanar. Now look at this chlorine. So we'll examine some of them. Let me examine this part. This chlorine is the leaving group, and this is the hydrogen, which is not anti-periplanar because these are in the same direction, dash dash. Now if I would have made it to this like this, but this is already given in there, this solid wedge. If solid wedge is there, this should be a dash position. So dash position is available for hydrogen, is not anti-periplanar. Not anti-periplanar to leaving group. Coming to this, again not anti-periplanar. Not anti-periplanar to leaving group. So the correct answer should be what? No product. It will give you no product. Another question. Predict the major product for the following reaction of elimination. So we have one equivalent of a base present over here. We have two leaving groups. One of them is iodine and one of them is chlorine. And we all know that among chlorine and iodine, leaving group ability is for all, whether it is SN1, SN2, E1 or E2, whatever the nature of reaction. This is fluoride has lesser than chloride, bromide, iodide. This is what we follow. I think my answer should be B. Only iodine will go because one equivalent of base is only given. If two equivalents would have been there, then both Cl and I could have gone. Next question, 2-bromobutane undergoes elimination via E2, blah blah blah. Find out the possible number of alkenes formed, including stereo. So first of all, let me form 2-bromobutane. 1, 2, 3, 4. And this is bromo. Now this will become CH. Then we have a strong base with us. Base has two possibilities to attack upon, because we all know this is alpha, this is beta, this is also beta. So these hydrogens will be attacked there. One compound will be CH2 double bond CH, CH2, CH3. This is Hofmann. Then what will be the ZF product? So guys, isn't it a stereo center? This is a geometric center actually, but this alkene is actually our ZF, and this ZF will also give you cis plus trans. So two alkenes are there, cis plus trans, and one is the Hofmann. The correct answer should be 3. B. So this is E1 versus E2 that we can compare. E1 reaction versus E2 reaction. So E1 reaction requires weak base, E2 requires strong base. Solvent should be good ionizing solvent. Basically, we require polar protic here, and we require polar aprotic here. Then order of substrate will be 3 degree, 2 degree, 1 degree only, and leaving group is better one required, better one required, and that is the same only, that fluoride, chloride, bromide, iodide. Talking about kinetics, it's a first order, it's a second order. ZF alkene is formed in both of them as measured. Stereochemistry, there is no stereo required because that happens with the first of all the carbocation is formed and then the alkene is formed. Here anti-periplanar structure is required, otherwise reaction will not work. Then some questions with us. 2-chloro-2-methyl pentane on reaction with sodium methoxide in methanol gives what? Well. First of all, what is it? 2-chloro CH3 CHCl, 2-methyl also. Okay, there is a 1-methyl. Pentane. So we are supposed to react on sodium methoxide, which is nothing but ETO minus a strong base. So where should it go and attack? This reaction is follow E2 reaction, so it will attack onto this. There is a possibility on this also, but this is minor. It will go here for major, and this will form Now check out the products, guys. Check out the products and pick the correct answer. Check out the correct answer. Zoop, 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 zoop. So it's a strong base, and we are supposed to attack on a 2 degree. So 2 degree will lead with the elimination only. That is what I want to say. So 2 degree gives mainly elimination. Not 2 degree, when it's at 3 degree. So only elimination will take place here. And sodium methoxide is strong base. So I think B and C should be the answer. What do you think? But B and C are not even the option. I think all of these are the correct answer. Okay. So mainly some very lesser part will be there. Some very lesser part will be there that will undergo substitution also. Some very lesser part is there that will go for substitution also. Anyways, not so great question. So now we have E1cB here with us, but before that we'll take a short break and then I'll come back and we'll rejoin. So we'll have a short break of 15 minutes. Those who haven't liked the session, 15-minute break and just don't go anywhere. Stay tuned.
को काफी ज्यादा डेवलप किया गया है एंड ये इम्पोर्टेंट हो जाता है क्योंकि सिंगल रिपोर्ट के अकॉर्डिंग काफी ज्यादा एलिगेशन और एप्लीकेशन लगाए गए थे अडानी ग्रुप को, जिससे अडानी ग्रुप के लिए ग्लोबली खराब चीज के साथ साथ काफी ज्यादा इम्पैक्ट आ रहा है। तो इस सेशन में हम कॉम्पिटिशन में डिस्कस करेंगे इस न्यू सिचुएशन के बारे में और साथ साथ हम भी जानेंगे कि इससे फ्यूचर हमारी कंट्री में क्या है। आपको कुछ नहीं करना, बस इस सेशन के अंदर बने रहना है मेरे साथ, क्योंकि हम ये पर्टिकुलर टॉपिक में है वो कॉम्पिटिशन स्टडी करता है एंड इकोनॉमिक्स की एक इम्पोर्टेंट केस स्टडी को अपने साथ पक्का करना है। तो सेशन में बने रहिए और हम फटाफट से चालू करेंगे। इंडिया का जो अडानी ग्रुप है उन्होंने इस इन्वेस्टमेंट को प्रॉमिस किया है जो यूएस सिक्योरिटी एंड इंफ्रास्ट्रक्चर के सारे प्रोजेक्ट में जो है वो इन्वेस्ट करेंगे। उसका प्राइमरी प्रोजेक्ट होगा वो 15,000 करोड़ का अनाउंसमेंट ट्विटर प्लेटफॉर्म पे किया गया है बाय हिज चेयरमैन गौतम अडानी, जिन्होंने कॉम्पिटिशन की डिस्कस किया वो कैसे करना है। हालांकि इस प्रोजेक्ट की कोई टाइमलाइन या कोई कमेंट नहीं किया, लेकिन इस पोस्ट को वेलकम किया गया बाय डोनाल्ड ट्रम्प एंड कि वो प्रॉपर एक्सेसिबिलिटी प्रोवाइड करने की कोशिश करेंगे अपने लैब पर, जिससे जो एनर्जी है और जो नए पाइपलाइन है जो नया इंफ्रास्ट्रक्चर है वो काफी इजीली डेवलप हो पाए एंड दोनों ही कंट्रीज के कोलैबोरेशन से एक क्लीन एनर्जी की तरफ, एक सस्टेनेबिलिटी की तरफ होगी। अब ये जो पूरा एंगल ऑफ डिस्कशन है वो इसलिए इम्पोर्टेंट है क्योंकि एक कंट्रोवर्सी जो है इंटरनल रिपोर्ट के अकॉर्डिंग काफी ज्यादा एक्टिविटीज लगाए गए थे अडानी ग्रुप से। ये इंटरनल रिपोर्ट में कहा था जनवरी 2023 जो अडानी ग्रुप है वो इम्प्रॉपरली यूज करता है ऑफशोर के लैंड को, प्रॉपरली मैनिपुलेट करता है और साथ साथ जो शेयर है उनमें भी घोटाला देखा गया। ये सारी जो एक्टिविटीज थे वो सही से लगा दिए गए वायरस अडानी को, लेकिन इसमें काफी ज्यादा प्रॉब्लम फेस करनी पड़ी को। हम देखेंगे कि मार्केट में इमेज टारगेट ठीक है, लेकिन इसके साथ साथ जो इकोनॉमिक वैल्यू थी वो भी काफी ज्यादा इम्पैक्ट हुई, अडानी ग्रुप को कुछ लॉसेस भी फेस करने पड़े। लेकिन ओवर द टाइम लेकिन ये भी जरूरी है वैसे ही एक इंडिकेशन देखेंगे कि अडानी ग्रुप का कमबैक हुआ है ग्लोबल मार्केट में, क्योंकि सुबह से बेसिकली रिपोर्ट का न्यूज आया था वहीं पे है जिसके चलते ही पूरा एंगल ऑफ डिस्कशन है वो इम्पोर्टेंट हो जाता है क्योंकि ये हमारी डेवलपमेंट होता है, क्योंकि हमारी कंट्री में एक तरीके से इमेज बेटर करने के आजकल में अगर हम डिस्कस करें कि इसके एडवांटेजेस क्या हो सकते हैं तो वो मैं लेकर आएंगे, लेकिन उससे पहले आप लोगों के लिए बहुत इम्पोर्टेंट आपको प्लेटफॉर्म का जो सब्सक्रिप्शन है जो अगर आपको यूएस इंडिया का टेस्ट न्यूज का एक्सेस मिलता है तो काफी जनरल अमाउंट में मिल रहा है, जो कि है 24 मिलता है। आपको करना कुछ नहीं है, बस सब्सक्राइब करना है और यूज करना है मेरा कोड राइट, जिससे आप अपनी यूपीएससी यूनिवर्सिटी प्रिपरेशन को स्टार्ट करेंगे। तो अब बेनिफिट को समझते हैं और इसके बाद वो एंड करती है क्योंकि बेनिफिट काफी ज्यादा इम्पोर्टेंट है और हमारे इकोनॉमिक्स के जो ये बहुत ज्यादा फायदा दे सकता है क्योंकि इस जो बेनिफिट्स हैं जो हमारी कंट्री को मिल सकते हैं ये है सबसे पहला जो इंडिया और यूएस मुझे वो टाइम यूज करने देता है। इसमें मार्केट में भी काफी ज्यादा इम्पोर्टेंट है, ये इकोनॉमिक वाइज जो है इसकी काफी ज्यादा डेवलपमेंट है, इससे फॉरेस्ट रिजर्व को इम्पैक्ट करेगा, इम्पोर्ट एक्सपोर्ट को इम्पैक्ट करेगा, इतना इम्पोर्टेंट चीज है। तो जो कोलैबोरेटिव एफर्ट है इसकी जो अपॉर्चुनिटीज है उससे भी फायदा आएगा, तो उस तक से करते हम देख पाएंगे कि हमारी साइज है वो बेसिकली कैसे हो जाएगी। आगे अगर हम पढ़ेंगे कि देखेंगे कि ग्लोबल रिजोल्यूशन और सॉफ्ट पावर जो है वो भी कंटिन्यूसली डेवलप होगा एंड ओवर द टाइम भी हम देख पाएंगे कि हर रिजोल्यूशन है कि हर कंट्री गेटिंग ओवर द टाइम बिकॉज यूनाइटेड स्टेट्स ऑफ अमेरिका बेसिकली ड्राइविंग फोर्स है और कंट्री की एलिमिनेशन है उसको ठीक करके हम यहाँ भी सिंपलीफाई करते हैं। ये जो हमारी एक्टिविटी है वो इकोनॉमिकली होगी एंड हमारी लर्निंग के बारे में बहुत मजबूत करेगी। जो इवेंचुअल फायदा है वो हमारा जो ऑलरेडी बात की गई वो भी होगा 16,000 करीब जो पोस्ट एडमिन ऑफ सब डिपार्टमेंटल की प्राइमरी होगा डॉक्यूमेंटेशन का क्राइटेरिया होगा वो भी दोनों को डिसाइड करेंगे। बट ऑल एट द सेम टाइम एनवायरमेंट अपॉर्चुनिटी प्रेजेंट हो जाएगी इस सबके साथ साथ हमको इकोनॉमिक गेन्स भी देखने को मिलेंगे टुवर्ड्स द एंड ऑफ द डे जो एफसीआई है पॉलिसी वो हमारी कंट्री में आते जाते रहेंगे अगेन हमारी जो कंट्री की इकोनॉमिक है जो हमारी कंट्री की सिचुएशन है वो बेटर हो जाएगी एंड कंट्री की रीजन है वो एक डेवलपमेंट वाली एस्पेक्ट की ओर बढ़ने लगेगी। अगला पॉइंट देखें तो बेसिकली इंडिया के जो गोल्स हैं वो भी सपोर्ट करेंगे और जो हमारा स्किल डेवलपमेंट है उसको भी इस पर्टिकुलर प्रोजेक्ट के चलते काफी ज्यादा काम देखने को मिलेगा। तो हम देख सकते हैं कि जो पूरी फील्ड है वो हमारे लिए एक ब्रिलियंट अपॉर्चुनिटी है जो कि हम यूटिलाइज कर सकते हैं बाय helping Basicity in America and by being there for it and by making this particular investment. So even if Adani Group का investment है लेकिन over the time अगर हम इन डेप्थ देखें इन सारे एडवांटेजेस हमारे लिए ला सकती है तो वो इन सारी एस्पेक्ट के अलावा भी अगर आपको कुछ और आता है ध्यान में जो हमें इस डील से बेनिफिट दे सकता है तो प्लीज टू मेक इट अ पॉइंट कि आप अपना जो ओपिनियन है उसको कमेंट सेक्शन में डाल दें अभी के अभी जैसे ही कोई पॉइंट आता है। और अगर आपको सेशन अच्छा लगा हो तो प्लीज लाइक जरूर करें। अभी तक सब्सक्राइब नहीं किया है तो सब्सक्राइब टू आवर चैनल लेट्स टॉक क्रिएटिव एंड इस सेशन को ज़्यादा से ज़्यादा शेयर करें ताकि ज़्यादा से ज़्यादा लोगों तक इस केस स्टडी पहुँचाई डेवलपमेंट लेवल समझ पाए क्योंकि हमारा जो आइडिया रहता है वो यही है कि आप अपने एग्जामिनेशन में कभी ना कोड को इतने अच्छे से यूज करें कि जो आपका एग्जामिनर है वो एट द फर्स्ट चांस ऑफ योर कॉपी आपको इम्प्रेस हो जाए एंड आंसर दे। अगर आपको सेशन अच्छा लगा हो तो हमारी चैनल के साथ बने रहिए क्योंकि हम बताते हैं आपके लिए सारे मिशन डेवलपमेंट अकेडमिक कोर्सेज और अकेडमिक इन्फॉर्मेशन। इसके साथ ही मैं नंदनी आज के लिए आपसे आगे बढ़ती हूँ। थैंक्स फॉर वॉचिंग।
Hi guys, I guess that was some healthy break we had, and let's come back everyone. Okay, so let me start. Now from here only two type of reactions have been listed. One of them is E1cB, highly important. Another one is EI, not so important. EI elimination, COP elimination. I haven't seen so many questions as such in past, even in JEE Mains and Advanced. But we'll try to cover everything so that at least we will come to know that elimination, all the reactions belonging to elimination have been covered till here. E1 versus E2 has been covered. Even CB we took an example meanwhile where we were studying about E2 reactions. So in the E2 reactions we saw that whenever any bulky group is there, then Hofmann product is achieved as a major product. In the other hand, we also studied whenever a leaving group is the poor leaving group. The leaving group is a poor leaving group such as fluoride, nitro group is there, cyanide group is there, which cannot be released easily. In that way, base attacks upon the beta hydrogen, forming an anion. A carbon ion is formed. Later on, by carbon ion, we have to check the stability of a carbon ion. The major carbon ion, the more stable carbon ion will give you the final product. Okay, I think this part is already covered. This is also covered already. Seems like it is repeated, guys. I'm sorry. So we'll directly go to the final one. Sorry. Okay, we can solve some questions. I can see some fresh new questions from here. So anyways, check this thing everyone. This is the fluorine, which is the poor leaving group. Because fluorine is a poor leaving group, this base can attack on that hydrogen first, which will give you more stable anion. But sometimes what happens everyone, we have a carbon ion formed and we can have that group attached with a ring, attached with the chain that can stabilize the carbon ion formed, such as, take this example, if we compare the stability of these two anion, so one will be formed here and one will be formed here, another can be this, now you can compare the stability of these two carbon ion and I find that this is in resonance and thus more stable. So although the reaction E1cB leads to the formation of SETZEF alkene, Hofmann alkene, but you can make SETZEF also as a major product when this kind of system is given, or I think this can give you the major product, will give you the major product. Conditions are already known. Electron withdrawing group, beta carbon must contain a presence of beta carbon like ketoaldehyde in order to stabilize the carbon ion. Presence of poor leaving group such as this, preferably presence of the strong base undoubtedly. This is some example which we see. ETO minus is attacking to the hydrogen. Okay, so we don't have any hydrogen with respect to this chlorine. So that is why the only option left is this one. It will form an anion. In the first stage, it will form an anion which is stabilized by the CF3 group present here. Then beta elimination occurs with removal of a fluoride group. And this chlorofluorocarbon will be your final product. This chlorofluorocarbon will be your final product. Next, write the correct product of this reaction. So see, we know that this might be the only option over here of beta is this. The hydrogen will be taken down, and we know the so formed carbon ion is resonance stabilized here, and that is why the reaction will keep on going under this direction. This is your slow step or RDS, followed by formation of an alkene. This is your product. And this alkene is also in the conjugation with this carbonyl group. So that is why also gives the extra stability. Next is, which of the following compound cannot give even CB? Okay, let me try. So this is fluorine, this is your alpha, this is your beta, hydrogen is there. Yes, it can give. We have an R3 here. So this is your alpha, we have beta also. So again, this is fluorine. So we have alpha carbon here, here beta hydrogen. But here we do not have, this will not go even CB, instead it will go for E2 rather than going for even CB, because even CB requires a poor leaving group to remove from there, or sometimes it requires the presence of some external stabilizing groups also, just like nitro is here to stabilize the negative charge will be appearing over here. So correct answer should be C. C doesn't have any poor leaving group simply. Which statement is correct about even? I think all we have covered this question, that electron withdrawing group facilitates the reaction so that it can stabilize the presence of the carbon ion. Formation of carbon ion takes place. Yes, leaving group of even CB reaction is poor. Which ester upon pyrolysis? Where we got this question? Ester. Well, pyrolysis will be taught later, but the correct answer is all. Isobutylene, CH3, C double bond O, O, CH2, CH2, CH3. So see everyone, what happens under these conditions, where basically this is EI reaction. Mistakenly this question came here. This is called as EI reaction. This becomes O minus, attacks upon the alpha, and this beta upon the beta hydrogen, attacks upon beta hydrogen. Beta hydrogen removes the electron density, puts it here. It forms the like this COO minus, and then hydrogen is already there. This become H, so it will become CH3 C double bond O, CH3 C double bond O OH, carboxylic acid, plus what was here? We had CH3, we have CH double bond CH2. So what is the meaning of isobutylene? CH2, CH2, CH3. Not giving isobutylene. See, this is the propylene I'm getting. 1, 2 and 3. So I think this is propylene which we are getting from the first A. Let me check it out for option number this will give C. So how does this happen? CH3, C double bond O, CH2, we have CH, then CH, we have 2 CH3 group here. Now this is, check it out everyone, how do we do it? This is called as pyrolysis of ester. This is oxygen, COOR. OR group must have alpha, this must have beta, hydrogen is there, this one, this has been attacked by the oxygen, and then electron density is gone to there. This bond departs, forming an acid. This is your acid, CH3COOH, which is an acetic acid, plus the product will be, look at this, CH2 double bond. So this is CH2 double bond, CH, not just CH, simply CH3 and CH3. So this is your isobutylene. Correct answer? C. C is the correct answer, not D. Chalo. Another question is here. AgNO3 is here and heat is also given. I think silver will help, this cation will help to generate a positive charge here, and then AgI will be separated out. Then is this reaction CH3OH as a base, it may come, and heat is given. That is why heat, look at the heat. So because of this heat, this is your hydrogen, this attacks upon the hydrogen, this is electron density goes here. So what would it make? No yaar, we haven't rearranged the carbocation yaar. The first product will be this, AgI will be deposited, this can undergo rearrangement. 1,2 hydride shift should I make? So it will go 1, 2 H minus shift and it will form a positive charge here. Then we can again go 1, 2 hydride shift, it will make a 3-degree carbocation. Then see, 3-degree carbocation is here. So at last your base, weak base is here. It can take too much time as possible. It's a weak base, it can take the time. Okay, it is asking that you do your rearrangement, I'll attack later, no problem. So we have plenty of options, but major option will come from this hydrogen. Oh! This hydrogen will be attacked by this hydrogen. This leaves the electron density like this, and the product will be, this is your product look like. Tell me where is the product like this. I think C is correct. C is correct. This is an example of even elimination. Now what, okay, C is the correct, na? Then fine. I was worried. This is already covered. Which upon pyrolysis, which you have already covered. Final topic of the day, everyone. Final topic of the day is EI reactions or EI eliminations. What is the meaning of EI? What is EI? EI is intramolecular elimination reaction. EI is what? Intramolecular elimination reaction. So intramolecular, or we also call it pyrolytic elimination or syn elimination, or there is one more name, we call it pericyclic elimination. Just try to understand what happens in this reaction. Read it out. So there are a number of organic compounds such as ester, acetates, xanthates, amine oxides, halides that undergo pyrolytic elimination. Pyro means heat. So you simply heat them, do not require any external agent. Just heat them and they will give you the eliminated product. And in the absence of adding reagent, inert solvent, absence of solvent, or in gas phase, in absence of solvent, just in gas phase, they form a cyclic state and they undergo elimination. So anyways, I'll explain this part to you. I'll explain the mechanism. So very simple, one step concentrated mechanism, one step. So one step mechanism. So see what will happen. It seems like we have studied it, but no, that was a different thing. That was, I remember, that was a quaternary salt and that was attacked by a base. That was E1cB. This is EI. Cope elimination is the first example. So what is happening here? If you heat this compound, this oxygen with negative charge attack on the beta hydrogen. This beta hydrogen leaves its electron density to this compound, this bond, and then depart this compound. So this is a 1, 2, 3, 4, 5. So how many members can you see, or let me just rewrite it. PH, CH, 1 hydrogen, CH2, nitrogen with a positive charge, CH3, then is the oxygen O minus. So now guys, this will attack onto this hydrogen. Now see, 1, 2, 3, 4, 5 members are there. Anyways, no problem. This is actually alpha, this is beta. Beta hydrogen only gives you the valid product, otherwise you will not get any product. Even you attack on the alpha or gamma, no product will be obtained. So this simply rearranges itself. This electron density goes here, this electron density goes to nitrogen, and there you get the product. So one of the product will be amino hydroxylamine, see, hydroxylamine, and the another product will be an alkene. So pH, we have CH, double bond CH2 plus CH3N, CH3OH, hydroxylamine. This reaction is called as Cope elimination, and we also call these reactions as EI eliminations. They move through EI elimination. So guys, these reactions also carried out with Hofmann product only is formed. So I want to mention this part that so usually Hofmann product is formed as measure as base oblique attacking group, sometimes O minus or S minus or whatever it is, attacks on syn side hydrogen, syn side beta hydrogen. So syn side beta hydrogen should be there, usually Hofmann, and not true always. Why? Because there is a possibility that in that molecule, if let us suppose the syn side hydrogen is not present, and syn side hydrogen is not there on the lighter group and it is present on the heavier group, then heavier will form and ZZ alkene will be formed as the major product. This happens. So anyways, let us take this example. So here CH2 is there, CH3 is there. See, we know that they should be in the same plane where we are attacking. So this elimination reaction is a syn elimination, and hydrogen atom leaving group depart on the same side. So we see, I don't see any hydrogen here. So here is the hydrogen, this is nitrogen, this is your nitrogen group, this is your alpha, this could be beta, this could be beta. So beta will be having same side, so this could be a same side, and this could be an opposite side of hydrogen. But sir, what we actually observe is we do not have too many options to attack upon, because this is actually this is NT, and this is in the same side, we call it syn. So this will attack onto this carbon, this hydrogen, the electron density removes here, then this group departs like this. Let us form the final product. We were expecting an alkene to be formed here, but finally the alkene will be formed here. So that is why we say it depends upon the mechanism where we exactly getting our hydrogen from, then we have to form the final product. This is how we get our final product, very simply done. And plus the next product will be nitrogen with OH, hydroxylamine, one CH3 and another CH3. I think now this part is absolutely clear to all of us. This reaction is called as EI reaction, COP elimination, and very simply I have explained all the parameters related to this reaction, where it should attack upon. Hofmann versus Setzef, Hofmann will be followed. But if Hofmann, if that hydrogen is not available on the same side, like this example, then you have to make this alkene. In the similar way, we have some more reaction. Like second, we can explain pyrolysis of esters. Pyrolysis of ester reaction is what? Simply heating the esters, but ester must have a beta hydrogen present on the OR group. So take this example. Let us suppose this is an ester. This is called as acetate ester. So O, CH2, CH2, CH3. Remember everyone, remember the necessary condition is very simple, that after this oxygen, this is alpha, this is beta. This is the only condition. Must have syn hydrogen, same side hydrogen to be attacked upon. So how would it basically work? Must have hydrogen. Yeah. What is the point of must have hydrogen, beta hydrogen? So how the reaction takes place? It's very simple, as I told you. This comes here, the electron density attacks onto beta hydrogen, hydrogen departs to give the electron density, this group leaves like this, O minus, final product will be CH3, C double bond O, OH plus, no, let me just explain it. This has become a single bond O minus, so it will become OH, this will be double bond O plus. Next will be CH2 double bond CH single bond CH3, an alkene will be formed like this. I hope we are getting it clearly, hopefully. Then the similar and third kind of example is called as pyrolysis of xanthate ester. Pyrolysis of xanthate esters. So what xanthate esters are? Xanthates are simple esters only, just with the sulfur atom is present there. So like right, so this is alkyl group, this is sulfur, this is carbon, This is double bond sulfur, this is oxygen, and the same thing will be happening over here, CH2 CH3, but again it should have a beta hydrogen over here. So equation is pretty simple. This is alpha, this is beta, and this sulfur attacks upon the beta hydrogen. The hydrogen departs and gives the electron density over here. This will be removed down like this. So the final product will be, what is the final product? RS C double bond. C is like SH here, and here is the double bond O, plus CH2 double bond CH2. Hofmann alkene will be formed mainly. So this is how the reaction occurs. And see, Hofmann, the concept of Hofmann and Setzef will not come in these cases, ester and xanthate ester, because you have just alkyl group which is attached with the oxygen that need to participate over here. But yes, it is very important and primarily used in the case of the N-alkyl amino oxide. There it is used. And there we end with every single question for today, everyone. Which of the following compound cannot give E1cB? Why this reaction repeated so many times? C is the correct answer. Which statement E1cB? I think all. Anyways, they are. So which ester upon pyrolysis? Now you can solve this question. Based upon the same concept, you can solve this question. So this is pretty much clear. Let us say if I talk about this oxygen. Check it out, everyone. This oxygen, I showed you how they react, how they work. This oxygen attack like this, electron density here, hydrogen departs, goes here, and no, not like that, like this. So what does it make? It will make CH3, C double bond O, OH plus CH2 double bond CH single bond CH3. So this is propene. So this is not correct. Now checking about isobutylene for second compound also, CH3OCH3. So basically this compound gives no pyrolysis as it doesn't have beta hydrogen. This is the alpha only. Now coming to this one, okay. This electron will be shown like this, comes here, attack here, then like this. So this is what the product will be obtained, CH3COH plus the C, H2 double bond C, CH3. Yes, everyone, this is your isobutylene group. This is very simple reactions. So this is what we do, and the correct answer is C. And with this we come to the end of today's lecture. I hope every one of you have enjoyed this lecture, and that is it for the day. So if you guys face any doubt, do let me know, I can help you. And if no doubt is there, then we'll wind up the session. Okay, in case of any doubt, do let me know. I'm taking your doubts from here. Ask me anything if you want to ask me. I'm sitting right now here. So guys, if you face any doubt, do let me know, else we are completed with all the reactions. Anyways, let me just give a brief again. Where were we? What we have covered? Today's major title was to finish two important reactions. One of them was substitution. Then we reached to the another reaction, elimination. In substitution reaction, we covered SN1, SN2, SNNGP, neighboring group participation, and SN intramolecular. Under this part, we covered unimolecular elimination, bimolecular elimination. Then we had unimolecular elimination reaction via conjugate base, and then we had intramolecular elimination reaction where we studied about the COP elimination, pyrolysis of xanthate ester and esters, and there we end with this complete reaction mechanism, right? So that is it.